Somewhere in the unfathomable darkness between the stars, something stirs. It's silent. It's invisible. It emits no light, no sound, no radiation, at least not the kind we can see or feel. But it's real. More real than most things we know. And it's coming this way. A black hole. But before we continue, subscribe to the channel and like the video. Imagine this. One morning, astronomers begin noticing strange distortions in the light from distant stars. A wobble in the orbit of a distant planet. Comets in the outer solar system behaving oddly. Data doesn't lie, and something is wrong. Very wrong. A gravitational monster is moving toward us, and it's closing the distance. Black holes are not just strange, they are terrifying. They are not objects in the traditional sense. They are places where the rules of the universe collapse in on themselves. Born from the death of massive stars or formed in the earliest moments after the Big Bang, these entities are cosmic singularities, points of infinite density wrapped in an event horizon from which nothing, not even light, can escape. There is no visible warning when one approaches. No flare. No smoke. No shimmer in the sky. Their arrival would be betrayed only by the way they twist space and time around them. And if one were to enter our solar system, the entire architecture of planetary motion, the delicate gravitational balance that keeps Earth orbiting safely around the Sun, would begin to break down. And it wouldn't even take a massive black hole to wreak havoc. Even a relatively small, stellar mass black hole, no bigger than a city but more massive than our Sun, could tear our solar system apart. We wouldn't notice it until it was already having an effect. The Oort Cloud, our first line of contact, would start to crumble. Comets would fall inward. The Kuiper Belt would be disrupted. Planets would feel the tug. Eventually, Earth itself would no longer be secure in its orbit. It might be flung into deep space. Or worse, it might spiral toward the black hole and vanish forever. And yet, paradoxically, if a black hole appeared in just the right place and speed, it might not destroy everything. It might become the new gravitational center of the solar system, a dark replacement for the Sun, cold, lightless, but stable in its own terrifying way. In this video, we're going to explore everything that would happen, step by step, if a black hole suddenly entered our solar system. This isn't just science fiction. It's a scientific thought experiment grounded in real physics. What signs would we see first? How would the outer planets respond? Could we survive the chaos? Is escape possible? And what, if anything, would remain? This journey will take us through the heart of darkness, through gravitational destruction, orbital upheaval, and possibly, the final moments of Earth itself. We will explore every phase of the encounter, from the first whispers of its arrival to the long echoes of its aftermath. Because the truth is, the universe is not a safe place. And black holes, they don't ask permission. In order to truly understand the threat posed by a black hole entering our solar system, we need to first understand what a black hole actually is. Not in the vague way popular media describes them, but in the brutal, raw reality of what they are in physics. At its core, a black hole isn't really an object, it's a place. A region in space where gravity has become so overwhelming, so absolute, that nothing, not even light, can escape from it. And that's just the beginning. A black hole forms when a massive star dies. As a star runs out of nuclear fuel, it no longer has the energy to counteract its own gravity. The outer layers explode outward in a supernova, while the core collapses inward. If the remaining mass is large enough, typically more than 3 times the mass of our Sun, it collapses beyond even neutron degeneracy pressure. The atoms themselves are crushed. The core implodes and forms a singularity, a single point of infinite density, wrapped in an invisible boundary known as the event horizon. The event horizon is not a surface in the traditional sense. You can't land on it, touch it, or bounce off it. It's a boundary in space-time, a point of no return. Anything crossing it is lost forever. And because no information, no light, no signal, no energy, can escape it, what lies inside is ultimately unknowable. Physics breaks down. Our equations fail. Time and space themselves cease to behave the way we understand them. Black holes don't suck things in like a cosmic vacuum cleaner. Instead, their gravity operates like any other mass, except they're incredibly dense. If our Sun were replaced by a black hole of equal mass, the planets would continue orbiting it as usual. The danger comes not just from gravity itself, but from how close an object can get before it crosses the threshold and disappears. What makes black holes truly dangerous is that they distort spacetime in extreme ways. Light curves around them. Time slows down dramatically near them. For an observer falling in, the universe outside speeds up. For an observer watching from a distance, the person falling in would appear to freeze in time at the event horizon. But that's just an illusion. Inside, they continue falling, and falling, toward whatever lies at the singularity. Some black holes spin. These rotating monsters drag spacetime around with them, twisting the very geometry of reality. Some emit deadly radiation through accretion disks, superheated rings of matter spiraling into oblivion. Some black holes merge with others, creating ripples in spacetime that we now detect as gravitational waves. But what matters in our scenario is this: a black hole is small, dense, invisible, and nearly impossible to detect until it's already influencing its surroundings. Even a black hole the size of a city could weigh more than the Sun and tear through our solar system like a blade through silk. Their danger lies in what they represent: a complete breakdown of the normal rules of the universe. They are the darkest possible outcome of gravity. And if one were to approach us, there would be no negotiating, no resisting, no diplomacy. It would be a confrontation between one of the universe's most unstoppable forces and the fragile stability of everything we call home. Black holes are not all created equal. They come in a variety of sizes and masses, each formed under different circumstances, and each capable of very different levels of destruction. To understand what might happen if one entered our solar system, we need to consider the different types, and ask which of them is most likely to be the intruder. The most common and well-understood type is the stellar mass black hole. These form from the collapse of massive stars, typically between 5 to 50 times the mass of our Sun. After a supernova explosion, the core of the star collapses into a singularity, leaving behind a black hole just a few kilometers across. Though small in size, their mass and density are immense. Thousands of these stellar black holes are believed to exist in our Milky Way, and some of them may be rogue, drifting through space after being ejected from their birthplaces. If one of these were to enter our solar system, it could easily disrupt planetary orbits, destabilize asteroid belts, and potentially swallow planets. It would be nearly invisible and silent, making it the most plausible and terrifying candidate. Then there are intermediate mass black holes, the cosmic middle children. Ranging from hundreds to thousands of solar masses, they are not as well understood. Few have been definitively observed, and their formation process is still debated. Some theories suggest they may form from the merging of multiple stellar mass black holes, or from the collapse of massive gas clouds in the early universe. These are much rarer, and their enormous gravitational influence would make them hard to miss. If one of these were entering our solar system, we would likely detect orbital anomalies and gravitational lensing far in advance. Their size and mass would mean catastrophe on a far grander scale. Even more immense are the supermassive black holes, which sit at the centers of galaxies. Ours, in the heart of the Milky Way, is known as Sagittarius A, and it has a mass of about 4 million suns. These titans span millions of kilometers and are the engines behind quasars and galactic dynamics. Fortunately, they don't roam. They are deeply embedded in the cores of galaxies, surrounded by vast clouds of stars and matter. The odds of a supermassive black hole drifting into our solar system are virtually zero. It would be like expecting a mountain to float into your neighborhood. But if it somehow did happen, it wouldn't just threaten Earth, it would annihilate the entire solar system, warping spacetime beyond recognition. Then there's a stranger possibility: primordial black holes. Hypothetical and never observed, these black holes are thought to have formed in the first fractions of a second after the Big Bang. If they exist, they could range in size from tiny atoms to massive objects. Some could have the mass of a mountain packed into the size of a proton. Because they're so small and emit very little or no radiation, they could be drifting through space unnoticed. One could even be in our solar system right now, buried deep in the asteroid belt or lurking near Neptune, exerting a subtle gravitational pull we haven't yet detected. Though less destructive due to their small mass, their extreme density could still cause bizarre phenomena, localized warping of space, disruption of spacecraft, or even slow erosion of planetary material over millions of years. So which one is most likely to enter our solar system? The answer is probably a rogue stellar mass black hole. Not too big, not too small, and common enough in our galaxy to be a credible threat. These black holes can be ejected from binary systems or star clusters and float freely through the Milky Way. There may be hundreds of millions of them, moving invisibly between stars. One such black hole, traveling at hundreds of kilometers per second, could be on a direct collision course with us, and we wouldn't know until its influence was already disturbing the fabric of our cosmic neighborhood. Its arrival would not be dramatic at first. There'd be no explosion, no impact, just an invisible distortion creeping across the edge of the solar system. And that brings us to the next terrifying truth: you wouldn't even see it coming. A black hole does not knock on the door when it arrives. It does not cast a shadow, emit a warning light, or produce a roar as it enters the solar system. Its most haunting trait is its silence. It is not only invisible, it is undetectable by any traditional means. And yet, it bends the universe around it. The arrival of such a thing into our solar system would not begin with fanfare. It would begin with confusion. Astronomers spend their nights looking at the sky, tracking tiny changes in the positions of stars, planets, and comets. They map the heavens down to the most minute movements, cataloging gravitational interactions, subtle light variations, and orbital paths. These meticulous efforts have given us the ability to detect the most distant exoplanets, track galaxies billions of light years away, and monitor asteroids only a few kilometers across. But a black hole, a stellar mass one, silently drifting between the stars, could pass through our line of sight undetected unless we were looking very carefully, in exactly the right way, at exactly the right time. Why? Because black holes do not emit light. They do not glow. Their defining feature is the event horizon, a boundary beyond which nothing, not even light, escapes. They are not just black in color, they are absent. They are invisible voids wrapped in intense gravity, detectable only by the effect they have on their surroundings. If a black hole were approaching from the direction of the galactic center, hidden behind dense fields of stars and interstellar dust, it could travel toward us unnoticed until it was close enough to begin tugging on things. But that's the key, tugging on things. Gravity is the first whisper of a black hole's arrival. Not its presence, but its influence. The first signs would be distant. At the far edge of the solar system lies the Oort Cloud, a vast, diffuse shell of icy objects, comets, and space debris extending nearly halfway to the nearest star. If a black hole began drifting toward us, its gravity would start disturbing this region long before it reached the inner solar system. Objects in the Oort Cloud, normally stable in their orbits, would start behaving unpredictably. Comets would fall inward, not in a steady, predictable rain, but in sudden waves, arriving in odd clusters, their trajectories not aligning with any known planetary influence. At first, scientists might blame gravitational perturbations from a passing star. That's happened before. Then they might consider a previously unknown planet, a so-called Planet 9. But as more and more anomalies accumulate, the models would stop fitting. Something massive and dark would be disturbing the balance. At the same time, astronomers might begin noticing unexplained movements in deep space probes. Voyager 1 and 2, which are far beyond the planets now, send back regular signals about their positions and velocities. If a black hole passed near their trajectories, even from a considerable distance, those paths would subtly shift. And these shifts, if modeled carefully, would begin to paint a picture, an invisible mass, of great density, moving inward. Another clue would come from the bending of light. As the black hole moves between us and distant stars, it would create a phenomenon known as gravitational lensing. This is when light from background stars curves around the black hole, producing temporary brightening, strange distortions, or duplicated images. These lensing events are rare, but they are measurable. We have already used them to discover otherwise invisible black holes roaming the Milky Way. A particularly sharp eye, using wide-field telescopes and long-term observation, might catch the telltale warping of starlight in the region of the sky from which the black hole approaches. But none of these signs would feel urgent, at first. There would be no blaring alarm, no countdown clock ticking ominously. The sky would look the same. The sun would still rise. Life on Earth would go on. Yet astronomers would begin to whisper. Papers would be published, debates held in quiet meetings. The mystery of the warped orbits, the altered light, the increasing common activity, these are the clues a black hole leaves behind, like fingerprints on glass. Eventually, computer models would reveal the truth: an invisible object, perhaps 10 to 20 times the mass of our Sun, moving toward the heart of our solar system. Its trajectory calculated, its speed measured. And then a horrifying realization: it's not going to pass by harmlessly. It's headed right for us. Or worse, it might be caught in a slow spiral toward the center of the solar system, destined to stay. Destined to become the new gravitational anchor around which everything revolves, or collapses. Public announcements would follow. News outlets would try to calm the public while experts scrambled to understand the timeline. How much time do we have? 1,000 years? 100? Decades? It all depends on its speed and distance. A fast-moving black hole could cross from the Oort Cloud to the inner solar system in a matter of centuries, or even less. A slower one might take millennia, quietly unraveling our cosmic neighborhood as it approaches. Meanwhile, strange things would begin to happen. Long-period comets would arrive in clusters never seen before. Their paths would defy all known models. Satellites in distant orbits might begin behaving strangely. The faintest ripple in the timing of planetary transits might be observed, tiny anomalies that scream of massive gravitational interference. And eventually, we would begin to see the stars themselves move, just slightly. Black holes don't emit light, but they distort everything around them. The background of the universe would begin to warp as the black hole comes closer. Stars would seem to shift position ever so slightly, not because they've moved, but because their light is bending. And still, to the naked eye, the sky remains unchanged. Imagine standing on Earth under a calm, moonlit sky, unaware that just beyond the reach of your senses, a black hole is creeping inward, silent, black, and unstoppable. No announcement from nature. Just a slow, steady invasion from the void. This is why black holes are so terrifying. They are not dramatic monsters storming through the cosmos with flashing lights and booming threats. They are quiet predators, stalking the galaxy unseen. Their arrival is a whisper. Their presence is a distortion. And their touch is absolute. By the time the black hole's gravity begins to pull on Neptune or shake the Kuiper Belt, it will already be far too close. And the next phase of its influence, the chaos that spreads inward from the solar system's edge, will begin. At first, the signs would be subtle, almost unnoticeable. But to the astronomers staring at the stars with cold precision, anomalies speak louder than light itself. When a black hole begins to influence our solar system, it doesn't announce its presence with fire or noise. It begins to tug, to bend, to twist the universe ever so slightly. These strange signals are the early warnings, the red flags fluttering on the edge of perception. One of the very first signs would be gravitational lensing, a warping of light caused by intense gravity. Einstein's theory of general relativity predicts that mass distorts space, and that distortion bends the path of light. Black holes, being so dense, bend light dramatically. If one passes between us and a background star, it can act like a lens, focusing and distorting the light of that star in a process called microlensing. From Earth, the star might appear to brighten, shift, or even momentarily split into duplicate images. These events are rare and brief, but we've already observed them elsewhere in the galaxy, revealing the presence of rogue black holes drifting through space. A microlensing event involving a black hole nearing our solar system would be studied intensely. It would give astronomers critical information: mass, speed, direction. The star whose light is being bent would be carefully monitored. Its position would jitter, and its image would distort ever so slightly. Such distortions could not be caused by any planet or asteroid. The math would point to something much larger, much darker, something with enormous gravitational pull but no light of its own. Then come the orbital anomalies. The planets of our solar system are watched with extreme accuracy. We know the orbits of Mercury, Venus, Earth, and the outer planets down to tiny fractions of a second. But suddenly, one of them begins to shift, just a little. A wobble. A drift. It might be Neptune or Uranus at first. Their distant paths are harder to model, but not impossible. If a massive object were influencing them from beyond, it would be measurable. The way a black hole's gravity pulls on the outer planets would slowly alter their orbits. Not in a dramatic way at first. But something in observatory, buried deep in data, would begin to suspect. Then Pluto and the Kuiper Belt objects would follow. The scattered icy rocks beyond Neptune, objects like Eris, Haumea, Makemake, would begin to misbehave. Their orbits would change direction. They might move slightly faster or slower. Some might seem to vanish from view altogether, thrown into new paths by the unseen hand of a black hole. Long-period comets, which usually obey predictable orbital patterns, would start arriving early, late, or in unusual trajectories. Their arrivals would seem clustered, as if something massive were pushing them in waves toward the Sun. Simultaneously, spacecraft would detect the shift. Voyager 1 and 2, New Horizons, and even distant probes like Pioneer 10 and 11, each one broadcasting back its position from billions of kilometers away, would reveal subtle anomalies in velocity. Not much. Perhaps only a few centimeters per second of unexpected acceleration. But even a shift that small, over time, becomes a signature. And with enough data, a model can be constructed. That model would point toward a source. An invisible source. A mass 10, 20, or even 30 times greater than our Sun, approaching from the dark. The signals would build slowly. Data from separate observatories, Chile, Hawaii, orbiting satellites, would all begin to converge on the same conclusion: an immense, compact, and completely dark object is altering the movements of distant solar system bodies. It is not a planet. It is not a star. It has no detectable atmosphere, no electromagnetic signature, no light. Only gravity. Soon, star catalogs would show distortions across larger regions. Not just one or two microlensing events, but an arc of space where stars seem to shimmer or bend subtly in position. These distortions would be mapped with extreme care. And then, scientists would find the epicenter. The dead center of the gravitational disturbance. And it would be empty. No visible object. No known mass. Just a void, surrounded by warped space and altered light. Panic wouldn't come immediately. Most people wouldn't even hear about it until much later. The scientific community would proceed cautiously, rechecking calculations, attempting alternative explanations. Could it be a cluster of dark matter? A collection of black dwarf stars? A previously unknown gas giant? But all other options would be ruled out. The mass required to cause the disturbances would be too great. The object would have to be too small to be a star and too massive to be a planet. The gravitational signature would be clear. The only known entity that fits this data is a black hole. And it's moving. The trajectory calculations would be the turning point. Once astronomers model the orbit and speed of the black hole, the reality sets in. It is not skimming by. It is not leaving the galaxy. It is approaching the solar system's heart. Perhaps not on a collision course with Earth, but close enough to warp every orbit, to fling entire planets, to collapse our cosmic stability. And still, to the naked eye, the sky looks normal. The sun rises. Birds sing. The oceans tide in and out. But the truth, now confirmed, would be shared in classified briefings, quiet meetings, and eventually the press. Journalists would be briefed. Agencies like NASA and ESA would prepare public announcements. The world would be told. And the questions would begin. Where did it come from? How much time do we have? What will happen to Earth? Can it be stopped? The early warnings were there all along. We just didn't know what we were seeing. Until it was too late. Now, with the mystery exposed and the black hole's presence confirmed, humanity stands on the edge of understanding its origins. What force hurled this monster toward us? Why now? And what secrets does it carry from the depths of the galaxy? When the presence of a black hole entering our solar system is finally confirmed, and the data no longer allows for any alternative explanation, the most pressing scientific question immediately shifts from what is it to where did it come from. Because while its impact may soon be our reality, its origin could hold vital clues, not just to its trajectory, but to the larger mysteries of the cosmos. A black hole wandering into our solar system is not just an astronomical event. It is a message from deep time. A relic of a story that may have started billions of years ago, perhaps before our sun was even born. There are several leading theories about where such a black hole could have originated, each one rooted in real physics and observational science. The most immediate and plausible explanation is that the intruder is the remnant of a nearby supernova, the collapsed core of a once massive star. Somewhere, not terribly far in cosmic terms, a giant star may have died violently, shedding its outer layers in a titanic explosion, while its core collapsed into a dense singularity. This remnant black hole might have existed peacefully for millions of years in a quiet binary system. But if that system was disturbed, perhaps by the gravitational nudging of another nearby star, or even by the explosion that created it, it could have been flung into interstellar space, severed from its original orbit. A stellar mass black hole traveling alone through the galaxy is not only plausible, but likely. Estimates suggest there may be as many as 100 million rogue black holes wandering through the Milky Way, completely invisible unless they interact with something else. One of these could have been slowly drifting toward us for eons, undetected, until it crossed the invisible threshold into our solar system's sphere of influence. Its path would be random, governed only by ancient gravitational interactions, perhaps the result of a stellar ballet that played out a billion years ago. In this scenario, the black hole isn't here because of us. We are simply in the way. But that's just the beginning. Another, more exotic theory suggests that this black hole could be an ejected member of a galactic core, flung from the center of a galaxy after a violent black hole merger. When supermassive black holes at the hearts of galaxies collide and merge, they can produce gravitational wave recoil, which, under the right conditions, can actually kick the newly formed black hole away from the center at thousands of kilometers per second. Some of these gravitational slingshots are strong enough to eject black holes completely from their host galaxies, sending them careening into intergalactic space like cosmic bullets. Most of those ejected would be supermassive and, thus, easier to detect. But it's not impossible for smaller black holes, intermediate in size perhaps, formed near the galactic core or in a dense star cluster, to be caught up in such chaos and flung into deep space. If the black hole in our scenario originated this way, it may have traveled for hundreds of millions of years, across the great empty gulfs between stars, finally arriving, by chance, in our quiet neighborhood. An ancient traveler, homeless, exiled by violence. An even stranger possibility lies in the realm of the early universe. This black hole could be primordial, a relic from the very first seconds after the Big Bang. Primordial black holes are hypothetical objects theorized to have formed from the collapse of high-density regions in the infant cosmos. At that time, the universe was not yet structured. Matter was not yet organized into stars and galaxies. But gravity already existed, and quantum fluctuations could have caused certain regions of space to compress beyond their limits, collapsing into black holes almost instantly. Unlike the stellar mass black holes born from stars, primordial black holes could vary wildly in mass, from as small as an asteroid to as massive as a planet or more. And crucially, they wouldn't require a star to form. They could be truly ancient, billions of years older than Earth, silently traveling through the dark ever since. If our visitor is a primordial black hole, then it might not just be dangerous, it might also be one of the oldest objects in the entire universe. A remnant of a time before stars, before galaxies, before light itself. This raises profound questions. Could such a black hole have passed by Earth before, in our planet's early history, unnoticed because it was too far away? Could it be responsible for unexplained disturbances in comet paths or cosmic radiation patterns we've observed but never understood? Could other such ancient objects be lurking even closer, still undiscovered? And then, there is the possibility that this black hole is a rogue wanderer, ejected from a system not because of a supernova, but due to gravitational instabilities in a dense star cluster. In regions like globular clusters, where stars are packed tightly together, massive interactions happen frequently. If 3 or more massive stars interact, the system can become unstable and throw one of the members away. In some cases, the result is a lonely black hole sent flying into space, stripped of any companion, unbound to any galaxy. This theory adds another chilling detail. This black hole may not be alone. It may have passed near other systems, other stars, disturbing their planets, scattering comets, possibly even triggering supernovae or star collapses indirectly through gravitational interference. What if the black hole has a history? A trail of destruction stretching behind it like the wake of a ship, invisible to us until now? Of course, all of these scenarios remain speculative until direct observation can narrow them down. Spectroscopy of nearby light distortions might reveal how fast the black hole is spinning. The pattern of lensing events might suggest how long it's been affecting the outer solar system. Even gravitational wave detectors like LIGO and Virgo might provide clues, if, by some slim chance, the black hole interacted with something else along its journey. But perhaps the most sobering conclusion is this: we may never know exactly where it came from. Its story could be written in a language that predates humanity, the solar system, and even our galaxy. We may only be the latest chapter in a tale that began long before there was even Earth to threaten. Still, while origin gives us insight, it does not grant safety. The fact remains, it is here. Or near. And with every passing year, it is getting closer. And now, with its presence acknowledged and its origin considered, attention turns to the outermost regions of our solar system, to the first of many casualties in this cosmic invasion. The black hole's influence is about to touch the Oort Cloud, and the ripple effects will begin to move inward. Far beyond the orbit of Neptune, beyond Pluto, beyond even the scattered icy debris of the Kuiper Belt, lies the first true frontier between our solar system and interstellar space, the Oort Cloud. It is not a defined shell like the rings of Saturn or a belt of neatly packed objects. The Oort Cloud is a vast, ghostly sphere of icy remnants left over from the formation of the solar system. Its exact size is unknown, but it is believed to extend from about 2,000 astronomical units (AU) from the Sun, roughly 200 billion kilometers, all the way out to 100,000 Australian dollars, nearly halfway to the next star system. This outer cloud is composed of trillions of icy objects, frozen relics from the solar system's birth. Many are no larger than mountains. Some are as small as boulders. Others are hundreds of kilometers across. They have spent the last 4.5 billion years in silence, barely touched, drifting in vast arcs under the weak influence of the sun's gravity. They are the forgotten leftovers of creation. But they are also the first to feel the touch of the intruding black hole. As the black hole draws near, the vast sphere of the Oort Cloud begins to distort. Its gravity may be pulling from thousands of AU away, but the sun's grip on these icy bodies is tenuous, weak enough that even a distant mass with enough density can overwhelm it. The perfectly balanced orbits of the cloud's residents begin to stretch. What was once a slow, predictable path now becomes an unstable arc. A slight nudge here, a stronger tug there, and objects that have not moved in millions of years suddenly awaken. Some of these icy bodies are pushed farther out, flung into interstellar space, never to return. But many more are drawn inward, like iron filings disturbed by an unseen magnet. They begin to fall, not in a straight line, but in a long, curling spiral toward the sun, obeying the strange gravitational ballet now unfolding. For astronomers on Earth, this would be one of the most obvious signs that something massive has disturbed the far outer regions of the solar system. Telescopes would begin detecting long-period comets arriving in greater numbers, in rapid succession. These comets, usually rare visitors from the deep solar wilderness, would start arriving in clusters. Their trajectories would be unusual. Instead of being randomly distributed, they'd seem to originate from the same general region of the sky, the direction from which the black hole is approaching. These sudden swarms would not just be a scientific curiosity, they would be a planetary threat. As these comets dive toward the inner solar system, their paths would bring some of them dangerously close to Earth. With so many objects falling inward, the probability of impacts increases dramatically. Earth has been struck before, by comets, by asteroids, and the results have been catastrophic. The dinosaurs were wiped out by a celestial impactor. Another, larger impact from one of these disturbed Oort cloud bodies could mean global disaster. And this time, it wouldn't be a one-off event. It would be a prolonged bombardment. Some comets would break up as they neared the sun, forming bright tails and spectacular displays in the night sky. To the casual observer, this might seem beautiful, harmless even. But behind that beauty would lie the terrifying truth: something massive is disturbing the outer boundaries of our solar system. Something powerful enough to reach across trillions of kilometers and stir ancient, sleeping debris from their frozen prisons. The Oort cloud, because of its enormous volume and its weak gravitational bonds, is like the skin of an egg, fragile and vulnerable. Once breached, the entire system inside is at risk. It acts as an early warning system, a cosmic tripwire. And the fact that it's being triggered means the black hole is now close enough to influence the most distant gravitational threads binding the sun's domain together. And as those threads snap, a chain reaction begins. Even without direct contact, the chaos unleashed by this first act, by this initial disturbance of the Oort cloud, can last for centuries. Some of the comets sent inward will take hundreds of years to complete their plunge, arriving in waves long after the black hole has passed. Others might be caught in new orbits, swinging dangerously through the solar system like scythes on a cosmic pendulum. Future generations could inherit these falling relics of destruction, long after the black hole itself is gone, or worse, after it has taken up a permanent place among the planets. The worst-case scenario is not that comets fall inward. It's that this is just the beginning. As the cloud's harmony breaks, the disturbance begins to move inward, toward denser, more structured regions of the solar system. Next in line is the Kuiper Belt, home to Pluto, Eris, Haumea, and countless other icy bodies. Here, the gravitational effects will no longer be subtle. Planets will wobble. Orbits will stretch. And what was once distant theory will become unmistakable evidence. Our solar system is unraveling. But it all started here, in the silent, frigid dark of the Oort cloud, a place so far from Earth that light from the sun is just a faint glimmer. A place where time stands still. Until, one day it didn't. The first victim has fallen. Beyond Neptune, beyond the scattered fragments of the outer planet's leftovers, lies the Kuiper Belt, a dense, icy ring of celestial debris circling the sun like an ancient moat. It stretches from about $30 to roughly $50, though its influence and spread can go much farther. This is the region where dwarf planets like Pluto, Eris, Haumea, and make live among billions of frozen bodies, some as small as pebbles, others as wide as continents. The Kuiper Belt is a graveyard of failed planets, an untouched relic of the solar system's formation. But now, that peaceful graveyard is about to be torn apart. The black hole's relentless gravitational pull, already having stirred the distant Oort cloud, now begins to sink deeper into the solar system. It approaches the Kuiper Belt, this ring of icy rubble, and with it comes instability. What was once the realm of slow-moving, stable orbits becomes a maelstrom of gravitational chaos. The balance, preserved for billions of years, begins to fracture. The first signs are the orbits. Objects that have followed predictable paths for millennia start to deviate. Pluto, once the ninth planet, now classified as a dwarf, begins to drift. Not by much at first. A slight tug here, a gentle wobble there. But over time, its orbital path starts to elongate unnaturally. It may shift closer to Neptune's path, or worse, cross into regions that destabilize both orbits. Planetary resonance, an intricate gravitational dance that has kept the outer planets from colliding, begins to falter. Smaller Kuiper Belt objects, KBOs, which number in the hundreds of millions, are more vulnerable. Their orbits are delicate, maintained by a careful interplay between their own momentum and the Sun's distant gravity. The black hole acts like a cosmic wrecking ball. Some objects are flung outward, ejected into interstellar space, never to return. Others are dragged inward, just like the icy bodies of the Oort Cloud, now turned into high-speed missiles destined for the inner solar system. To astronomers on Earth, the Kuiper Belt would light up, not with fire or brilliance, but with motion. Telescopic surveys would reveal unprecedented activity. KBOs once thought lost or stationary would reappear on strange, high-inclination orbits. Some would seem to spiral in wildly, crossing the orbits of outer planets and threatening catastrophic encounters. The gravitational relationships among the distant worlds begin to decay. Pluto's 3:2 resonance with Neptune, which has kept them from ever colliding, might snap. If the black hole's influence is strong enough, Pluto could even be nudged into an orbit that crosses Neptune's at just the wrong angle, potentially leading to long-term instability that could end in a collision or ejection. But Pluto is not the only victim. Eris, more massive and further out, might experience even more extreme orbital changes. Haumea, with its bizarre, elongated shape and ring system, could be torn apart if caught in the wrong gravitational moment. Whole families of KBOs, groups of icy objects that share a common ancestry from long-ago collisions, could be disrupted, scattered into the solar system or sent to oblivion. In addition to the orbital chaos, tidal effects start to emerge. Though less extreme than those experienced by moons or planets close to stars, even the weaker tides felt in the Kuiper Belt could cause stress fractures on some icy bodies. Slowly rotating dwarf planets might start to spin erratically. The fragile crusts of ancient objects could crack open, releasing plumes of gas and dust that briefly light up like comets. It would be the first time many of these distant objects show activity in billions of years, a violent awakening from deep space slumber. For planetary scientists, it would be a scientific revolution. New data, new motion, fresh mysteries. But under that wonder would lie the horror of knowing that these changes are not part of a natural cycle. They are the death throes of a region under siege. And what's more, the chaos is moving inward. The black hole's journey is not yet finished. The Kuiper Belt, though more massive than the asteroid belt and rich with ancient material, is still composed of small, fragile bodies. Once this outer ring is disrupted, the gravitational influence will begin to be felt by the true giants of the solar system, the ice giants, Uranus and Neptune. And that's when the game changes entirely. Because now, we're no longer talking about small icy rocks. We're talking about planets, massive, gaseous, magnetically active worlds. If a black hole can destabilize them, the consequences for the entire solar system could be unimaginable. But even before that, the Kuiper Belt continues to unravel. Each disrupted orbit sends new comets and debris inward. Each gravitational tug increases the instability of the outer system. The ancient boundary between our solar system and the stars beyond is collapsing. The gate has been breached. The wild winds of interstellar gravity are rushing in. Back on Earth, scientists race to keep up. Simulations, run on the world's fastest supercomputers, reveal grim predictions. The Kuiper Belt's debris will flood the inner solar system over the next few centuries. Some fragments may reach Earth's vicinity in mere decades. Others, larger than ever imagined, could be on a trajectory of destruction. And this is just the echo of a much larger force still coming closer. The once static maps of our solar system are no longer accurate. The lines we drew to explain the calm and order of our cosmic neighborhood are being redrawn, distorted, erased. And the cause of it all, the black hole, remains invisible, silent, and unstoppable, continuing its descent into the realm of the planets. Neptune and Uranus, long guardians of the outer solar system, orbit the Sun in stately silence, massive, frigid giants that have drifted through space for billions of years. Their swirling atmospheres and distant moons paint a picture of serene alien majesty. But serenity has a weakness. It's only as stable as the forces holding it together. And as the invisible black hole draws closer, these distant titans begin to feel the first subtle hints of disruption, tugged by a hand they cannot see. The earliest signs aren't cataclysmic. They're mathematical. Planetary scientists, continuously tracking the orbital periods of Neptune and Uranus with immense precision, begin to notice slight deviations. The positions of these planets, which once aligned perfectly with predictive models, start to drift, first by tiny fractions, then by larger margins that can't be dismissed as observational error. Something massive is disturbing the outer planetary orbits. And it's not any of the known celestial bodies. For Uranus, already tilted on its side due to some long-ago cataclysm, the tug of a rogue black hole could reignite its chaotic past. Uranus's orbit begins to elongate, stretching it farther from the Sun at one end of its journey and pulling it closer at the other. As its distance from the Sun changes, so too does the duration of its seasons, already extreme due to its axial tilt. These shifts would take decades to unfold, but the effects would begin to destabilize the system of moons that orbit it. Moons like Miranda and Titania, once in graceful resonance, might start to drift apart or fall into eccentric orbits. Gravitational stress between Uranus and its moons could cause tidal heating, cracking ice crusts, stirring subterranean oceans, awakenings of internal activity after eons of deep freeze. Neptune, the outermost of the traditional planets, holds the solar system's edge like a cosmic lighthouse. But even this distant sentinel is not immune. Its own orbit starts to twist and bend, pulled by the same invisible force affecting Uranus. Neptune has its own system of moons and one particularly infamous companion, Triton. Believed to be a captured object from the Kuiper Belt, Triton orbits Neptune in retrograde, opposite the planet's rotation. It is already a gravitational oddity, slowly spiraling inward. But now, under the warping influence of the black hole's gravity, Triton's descent accelerates. There is a possibility, however remote, that this icy moon might one day crash into Neptune, or be ripped apart to form a new ring system. Both Uranus and Neptune serve a delicate role in the structure of the solar system. Their gravitational influence has helped shape the paths of comets, the placement of the Kuiper Belt, and even the orbital resonances of smaller bodies. As their orbits distort, the ripple effect spreads. The delicate harmony of motion across the solar system begins to fall out of tune. Other planets, even those closer to the Sun, start to feel the echo of this imbalance. If the black hole's trajectory brings it close enough to these giants, the consequences escalate. In the worst-case scenario, either planet could be flung into a new orbit, one that brings it dangerously close to the inner planets, or perhaps ejects it entirely from the solar system. Though this would require an extremely close approach, even the possibility is terrifying. A gas giant on a rogue path would be a cosmic wrecking ball, disturbing every gravitational relationship it crosses. Even without such a dramatic fate, the gradual unraveling of their orbits means one thing is certain: the solar system we know is ending. It might not be an explosion. It might not be a scream. It might be a slow, gravitational unraveling, like a tapestry coming apart thread by thread. This phase of the black hole's invasion marks a turning point. The disturbances are no longer limited to comets and dwarf planets. Now the giants themselves, the ones that help form and protect the structure of the outer solar system, are being dragged into chaos. The protective barrier they provided against deep space debris is weakening. Their ability to shepherd objects and maintain cosmic order is fading. And as they lose their grip, the gravitational cascade moves inward. Soon, it will be Saturn's turn. With its majestic rings and complex system of moons, it too stands on the edge of chaos. The black hole is still moving, still pulling, still warping the very fabric of space as it approaches the next victim in line. Saturn, the jewel of the solar system, floats like a cosmic sculpture in the vacuum of space. Its massive bulk, banded in pastel hues, is surrounded by the most iconic feature in our celestial neighborhood, a vast system of rings made of ice and rock, stretched across hundreds of thousands of kilometers. These rings are delicate and complex, a fragile dance of countless particles, each orbiting in perfect harmony, maintained by the subtle tug of Saturn's gravity and the shepherding of its moons. But that harmony is about to be broken. As the black hole edges closer to the heart of the solar system, its gravitational influence reaches Saturn. Unlike Neptune and Uranus, which have largely spherical structures and comparatively thin rings or tilted axes, Saturn's ring system is more vulnerable, more exposed. The rings are held together by a balance between Saturn's pull and the orbital velocity of the particles within. It's a system that thrives on stability. Even slight gravitational interference from the outside can turn order into chaos. At first, it would be almost imperceptible. High-resolution observations from orbiters like Cassini, if they were still active, or from Earth-based radio telescopes would notice strange motions in the rings. Some areas begin to thicken, others to thin. Particles that once moved in resonance begin to drift out of alignment. The shepherd moons, which keep the rings tidy by orbiting just inside or outside the bands, would feel the warping of their own paths. Their gravitational nudges would fall out of sync, allowing ring particles to spread, collide, and fragment. Then come the tidal forces. A black hole doesn't have to come close to physically touch Saturn or its rings. Its tidal forces, the difference in gravitational pull from one side of Saturn to the other, can act across immense distances. These forces start to tug more strongly on the outer edges of the ring system than the inner regions. The result, a slow, stretching tension that pulls the ring particles apart from each other. The particles begin to accelerate and decelerate unevenly, and as their delicate balance breaks down, so too does the structure of the rings. Collisions begin to happen. Not with dramatic explosions, but with quiet, relentless frequency. Ring particles slam into each other at slightly different velocities, generating shockwaves of dust, scattering fine ice crystals into expanding clouds. The rings, once distinct and neatly separated into structures like the A, B, and C rings, begin to blur. Sharp divisions like the Cassini division grow less defined. Gaps close. Edges smear. The symmetry that once made the rings so mesmerizing starts to vanish. If the black hole draws close enough, the disruption grows violent. Some fragments of the ring system may be flung away from Saturn entirely, caught in the competing gravity wells of Saturn and the intruding black hole. Others may be pulled inward, raining down on the planet like frozen meteors. Saturn itself might begin to glow faintly in infrared as infalling ring material heats its upper atmosphere. The system that had remained largely unchanged since before the age of the dinosaurs starts to dissolve in real time. Meanwhile, Saturn's moons, Titan, Enceladus, Rhea, and others, begin to drift. Their orbits, finely tuned by millions of years of gravitational interaction, respond to the distant black hole like a ballet troupe thrown into confusion by a hidden puppeteer. Tidal forces stretch and compress them, triggering internal heat, increasing volcanic and geyser activity. Enceladus, already known to shoot plumes of water vapor from its surface, could erupt more violently. Titan, with its thick atmosphere and methane lakes, might see atmospheric shifts or surface changes as its orbit warps. Some moons may collide. Others may be ejected. And then there is the possibility that parts of the ring system, once broken and scattered, may begin to reform, not into rings, but into temporary clumps and protomoons. The gravitational chaos can cause localized accretions, where debris fuses rather than disperses. But these would be short-lived, quickly torn apart by the fluctuating gravity of Saturn and the black hole. To observers on Earth, these events would unfold gradually at first, but with increasing pace. Images of Saturn's iconic rings would begin to change, no longer symmetrical bands, but shredded arcs and disrupted waves. Scientists would struggle to keep up with the modeling. What was once the most visually stunning structure in the solar system would now be a haunting monument to gravitational collapse. Saturn itself, massive and distant, will endure longer than its rings. But this stage of the black hole's intrusion marks another irreversible step in the unraveling of the solar system. The loss of Saturn's rings is not just an aesthetic tragedy, it's a signpost. The outer solar system is gone. Its structure has collapsed. Now, the black hole's influence is marching inward, toward the realm of the giants, toward Jupiter. And with that, the solar system's fate becomes even more precarious. Jupiter, our solar system's colossus. the king of planets. A swirling, gaseous behemoth more massive than all the other planets combined. With its turbulent storms, roiling atmosphere, and powerful magnetic field, Jupiter has long been considered Earth's silent guardian. Over the course of billions of years, its immense gravity has deflected or consumed countless comets and asteroids that might otherwise have slammed into our planet. It's a shield, a wall, a protector standing between us and the chaos of the outer solar system. But now, that shield may itself be under threat. As the black hole continues its inexorable descent into the heart of the solar system, the protective role of Jupiter is put to the ultimate test. Unlike Saturn's shattered rings and the skewed orbits of Neptune and Uranus, Jupiter represents the first planet in this spiraling catastrophe whose mass rivals the scale of the threat, albeit in a vastly different form. If any body is capable of resisting the gravitational chaos brought by the black hole, it's Jupiter. But the question arises, will Jupiter be Earth's last line of defense, or the black hole's next meal? At this stage in the black hole's approach, its gravitational influence has crossed a threshold. The inner gas giants are now directly in its grasp. While the Sun still dominates the inner solar system, the black hole's competing pull is rapidly distorting the balance. The space between these two colossal gravitational wells becomes a battleground of forces. And Jupiter, as the most massive object orbiting the Sun aside from the Sun itself, becomes the focal point of that struggle. To understand the stakes, we must first consider Jupiter's immense gravitational pull. It has been the solar system's great recycler of debris. Many long-period comets that might have been on Earth-crossing paths were intercepted by Jupiter, either slung harmlessly out of the solar system or swallowed whole. Its massive magnetosphere, too, plays a role, trapping radiation and particles, shielding the inner planets from some of the charged chaos hurled through interplanetary space. But as the black hole's tidal forces escalate, Jupiter's influence begins to fluctuate. The balance it has always maintained with the Sun is thrown off kilter. Jupiter's orbit begins to distort, perhaps slightly at first, becoming more elliptical. This alone causes cascading effects. The trajectories of its moons shift, and its gravitational influence on surrounding asteroid belts begins to change. But more alarmingly, the gravitational interplay between the Sun and the black hole creates a moving tidal node in the solar system, regions of intense gravitational stress, like overlapping waves. If Jupiter happens to pass through one of these nodes, the effect could be catastrophic. The possibility of Jupiter being captured into an unstable three-body interaction becomes very real. These chaotic gravitational interactions, known as causative oscillations, can cause massive shifts in inclination, eccentricity, and orbital energy. Jupiter, instead of moving in a relatively flat and circular orbit, could be tipped, pulled, or accelerated in unexpected directions. It may be driven into a new, more elongated orbit that intersects with those of other planets, threatening chain reaction instabilities. Worse still, if the black hole's approach is direct enough, Jupiter might find itself on a decaying orbit, not around the Sun, but around the black hole. If that happens, we could witness something no human has ever seen, a gas giant falling into a black hole. The mechanics of such an event are terrifying. As Jupiter gets too close, it would begin to experience spaghettification, the process by which objects are stretched and compressed as they approach the event horizon of a black hole. But because Jupiter is not a solid object, this process would look very different from what would happen to a rocky planet. The upper atmosphere would be the first to be stripped, its hydrogen and helium layers pulled into long, spiraling streams of gas, glowing faintly as they accelerate and heat up. These streams would form an accretion disk around the black hole, glowing in X-rays and radio waves, betraying the presence of the invisible devourer. Jupiter's moons, over 90 of them, would suffer their own fates. Ganymede, the largest moon in the solar system, could be ejected into deep space. Io, with its volcanic Hell's Cape, might be torn apart by tidal stress. Europa, that icy moon with a hidden ocean, might be shattered entirely, spewing water and ice into the vacuum in a final, frozen geyser. However, it's not guaranteed that Jupiter would be consumed. It might, under specific orbital conditions, act as a gravitational shield, absorbing or deflecting incoming debris flung in from the outer system. Just as it has done for eons, Jupiter could once again intercept comets and asteroids destabilized by the black hole's approach. In fact, the increased number of objects spiraling inward, drawn from the Kuiper Belt and Oort Cloud, might result in a deadly bombardment on the inner solar system, one that Jupiter partially mitigates through sheer gravitational dominance. In this role, Jupiter would be buying Earth precious time, intercepting doomsday projectiles and keeping the flood of debris from reaching the terrestrial planets, at least temporarily. But being a shield doesn't make Jupiter invulnerable. Even if it isn't captured or consumed, Jupiter may still be radically altered. Its magnetosphere could be warped, exposing its inner moons to lethal radiation. Its bands and storms, especially the Great Red Spot, might behave erratically as atmospheric currents adjust to new gravitational conditions. New jets and vortices might form, visible in high-speed atmospheric simulations. Planetary scientists would watch in horror as Jupiter's stable, familiar features dissolve into new and chaotic forms. From Earth, powerful telescopes would track these changes. Astronomers would see the planet begin to shimmer in the infrared as its atmosphere is heated unevenly. They might even detect faint radio signals, emissions caused by the stretching of magnetic field lines or the interaction of its moons with destabilized plasma flows. Eventually, a tipping point would arrive. If the black hole's trajectory continues inward, Jupiter will no longer be able to resist. It will either fall in, creating a final, brilliant flare of radiation before vanishing entirely, or it will be flung outward, away from the Sun, transformed into a rogue planet hurtling through space. Either fate would be apocalyptic for the solar system. If Jupiter is swallowed, Earth and the inner planets lose their shield. The next waves of debris, asteroids, icy fragments, maybe even destabilized moons, will have a direct path inward. The rate of bombardment on the inner planets will increase dramatically. Earth could become a target in a renewed age of impacts, each one potentially extinction level. If Jupiter is ejected, it becomes a new threat. A free-floating mass, larger than 300 Earths, barreling through the solar system. If it swings back inward on a destabilized path, it could collide with another planet, rip moons out of orbit, or distort the entire gravitational architecture of the solar system. The loss of Jupiter would mean the collapse of every resonance it helped maintain, from the asteroid belt to Mars stability, to even the gentle balance between Earth and its own moon. And yet, there is one glimmer in this unfolding nightmare. Because Jupiter is so massive, so dominant, there's a possibility that it could capture the black hole temporarily into an orbit, a bizarre binary system of a gas giant and a black hole, locked in mutual motion around each other, like dancers in a dark waltz. This could delay the black hole's descent into the solar system's core, buying the inner planets time to prepare, to react, or even to attempt the unthinkable, escape. But if this waltz begins, it won't last long. The black hole is relentless. It will either fall inward or fling Jupiter outward. And once that decision is made, the battle for the solar system will move past the giants and into the realm of the inner planets. The next victim will not be a distant gas world. It will be Earth's closest neighbors. It will be us. The moment Jupiter falls, whether consumed, ejected, or simply destabilized, marks a profound turning point. It is no longer a question of if the solar system will survive, but how long it will take to come undone. The gravitational linchpin of the outer planets is gone or distorted, and the ripple effects of this event travel like invisible shockwaves through the fabric of space-time, reaching inward toward the terrestrial planets. The order that has governed the solar system for 4.5 billion years, steady, graceful, seemingly eternal, begins to break apart. Each planet, from Mercury to Neptune, relies on a precise balance between inertia and gravity to maintain its orbit. The sun's pull keeps them circling, while their forward momentum keeps them from falling inward. But when another massive object, like a black hole, enters the solar system and begins competing for gravitational dominance, that balance unravels. Orbits shift. Periods change. Inclinations wobble. Some planets begin to spiral inward, others are pushed outward. Resonances collapse. The geometry of the solar system distorts like a spiderweb caught in a windstorm. The first visible signs of this unraveling would come in the form of orbital anomalies. Earth, Venus, and Mars begin to deviate from their expected positions. Transits across the Sun shift slightly. Seasons start to arrive early or late. Day lengths stretch or compress by milliseconds, small but measurable, and these irregularities accumulate quickly. Lunar eclipses no longer align perfectly. The Moon's orbit around Earth begins to warp, its distance fluctuating in ways that disrupt tidal patterns and cause strange oceanic behaviors. Meanwhile, Mars, already lightly tethered to the Sun compared to the inner planets, experiences the most dramatic shifts. Its orbit stretches into a more eccentric ellipse, occasionally drawing it dangerously close to Earth's path. Over centuries, these near misses could become true intersections, risking future planetary collisions or gravitational encounters capable of flinging Mars into a new orbit entirely. Even Venus, with its thick atmosphere and hellish surface, begins to show the effects. Its rotational period, already unusual, spinning retrograde and incredibly slowly, may become more erratic under the fluctuating tidal forces from both the black hole and a now unbalanced Sunday. Atmospheric tides become stronger, perhaps even increasing volcanic activity beneath its surface or thickening its runaway greenhouse effect. Venus might become more unstable, more hostile, or even suffer internal collapses as a result of gravitational stretching. But Earth is where the collapse becomes personal. As our planet's orbit distorts, so too does everything we depend on. The length of the year might increase or decrease slightly. That would be enough to throw off agriculture, climate systems, and even the structural integrity of satellites and space stations that rely on precise orbital mechanics. Gravitational fluctuations could create lunar tidal surges, increasing the power of ocean tides to the point where coastlines are routinely flooded. Earthquakes might become more frequent as the mantle flexes under tidal strain. Volcanoes, especially those with massive magma chambers like Yellowstone or Campi Flegrei, could erupt due to changes in internal pressure. And the black hole is not even at its closest yet. As it draws nearer, one or more of the inner planets may collide. This is not a hypothetical or a science fiction trope, it's a legitimate outcome of severe orbital destabilization. Simulations show that, under the right conditions, a wandering object disrupting Jupiter or Saturn could cause Mercury to crash into the Sun or Mars to collide with Earth within a few million years. But a black hole speeds this process up drastically. The timescale shifts from millions of years to thousands, or even hundreds. The inner solar system becomes a high-speed demolition derby. Planets no longer glide gracefully around the Sun, they lurch, wobble, and twist like drunk dancers spinning toward their doom. Gravitational interactions between Venus and Earth grow tense. If their orbits cross too closely, the possibility of one planet gravitationally slingshotting the other increases. One could be ejected entirely, the other pulled inward toward the Sun or the black hole. And if they collide, the result would be a planetary-scale cataclysm, a release of energy billions of times more powerful than the largest nuclear weapons ever imagined. Both planets would be obliterated, reduced to molten wreckage that would eventually coalesce into a new, hot debris disk. This is what unraveling looks like. Not with a bang, but with a series of slow, crushing escalations. With tiny irregularities snowballing into tidal chaos. With once predictable orbits turned into serpentine paths that cross and threaten each other. With moons lost, atmospheres stripped, surfaces shattered, and planetary bodies thrown into death spirals they cannot escape. The solar system is no longer a place of celestial harmony, it's a battleground of gravitational survival. And amidst the chaos, one force looms larger and darker than all the others, the black hole. Still silent, still invisible, but with every passing moment it comes closer. It has not yet reached the inner planets, but its presence is felt in every distorted orbit, every collapsing resonance, every moon flung into deep space. It's the center of the storm, a void of inevitability. In the aftermath of Jupiter's destabilization, we see the consequences ripple through every orbit and every body. The asteroid belt begins to shift. The Trojans and Greeks, asteroid clusters and Jupiter's Lagrange points, lose their anchor and disperse. Their scattered remnants begin falling inward too, another wave of chaos heading for the terrestrial planets. The solar system we once knew, a system of predictable paths, reliable seasons, familiar skies, is disintegrating into something primal and lawless. A place where planets no longer follow rules. Where stability is an illusion. Where Earth, once safely nestled in the Goldilocks zone, is now teetering on the edge of disaster. And the worst is yet to come. Because as the black hole moves ever inward, Earth's own orbit, the very path that defines life on our planet, is about to be directly affected. As the black hole continues its inward crawl, passing the gravitational landmarks of Neptune, Uranus, Saturn, and Jupiter, each twisted or shattered in its wake, it finally sets its invisible eye on the realm of the inner solar system. And now, its influence, once distant and subtle, reaches Earth directly. Our planet has long thrived within a delicate, life-supporting balance, an orbit shaped into near perfection, keeping us within the Sun's habitable zone, the so-called Goldilocks region, not too hot, not too cold. It is this orbit that controls the rhythm of our lives, the seasons, the tides, the length of a day, the stability of climates. But that rhythm is now beginning to shift. The black hole's gravitational pull, competing with the Sun's, begins to distort Earth's orbit in ways that will change everything. At first, the distortion is minuscule. Earth's orbit, which has always been slightly elliptical, becomes just a little more elongated. We start to drift a bit farther from the Sun at aphelion, and swing a bit closer at perihelion. The consequences seem small. Seasonal temperatures begin to vary more wildly. Summers become hotter and more extreme, winters colder and longer. But these are only the first ripples of a far deeper disturbance. Over time, weeks, months, years, the changes accelerate. As the black hole gets closer, Earth's orbital eccentricity increases dramatically. Instead of a gentle oval-shaped path around the Sun, our trajectory becomes a stretched ellipse. In some parts of our orbit, we are now much closer to the Sun than ever before, causing periods of intense heat, drought, and megastorms. In others, we drift so far out that Earth begins to cool catastrophically, plunging into temporary mini-ice ages. This uneven exposure to solar radiation wreaks havoc on global weather systems. Monsoons fail. Polar ice melts and then refreezes with savage speed. Ocean currents collapse and reform in alien patterns. Agricultural zones vanish. Entire ecosystems blink out of existence. Humanity, still clinging to fragile infrastructure built for a stable Earth, begins to buckle. Meanwhile, Earth's axial tilt, once kept in check by the stabilizing pull of the Moon and subtle nudges from other planets, starts to wobble. With Jupiter's orbit destabilized and the Moon's own path affected, Earth enters a period of axial chaos. Our planet's tilt might swing by several degrees, wildly altering where sunlight falls across the globe. Regions that were once temperate become tropical. Equatorial zones may find themselves trapped in endless dusk. The poles, long accustomed to periods of total darkness or light, might flip their identity altogether. The calendar loses meaning. Traditional seasons are replaced by unpredictable cycles of temperature extremes. And then comes the effect on the length of a day. Tidal forces from the black hole, though distant, begin to tug on Earth's rotation. The Moon, which helped slow Earth's spin over billions of years, is now itself destabilized. If the black hole begins drawing more gravitational energy from the Earth, Moon system, Earth's rotation could either slow down more rapidly or, if angular momentum is distorted, speed up. A day that once lasted 24 hours might stretch to 30, or collapse to 18. Circadian rhythms fail. Biological clocks are thrown into disarray. The tides, too, begin to behave unnaturally. No longer governed solely by the Moon's pull, they now feel the distant influence of the black hole. The result is supertides, vast, planetary-scale waves that consume coastlines, flood cities, and reshape continents. Ocean water, sloshed about by chaotic gravitational interference, surges inland unpredictably. Some coastal cities become uninhabitable. Others are lost entirely beneath the waves. But the damage doesn't stop at the surface. The Earth's crust, always under internal pressure, begins to feel new, inconsistent stress from tidal stretching. This strain leads to a surge in seismic and volcanic activity. Earthquakes become more frequent, more intense. Dormant volcanoes awaken. Supervolcanoes, like Yellowstone, are pushed closer to eruption thresholds as mantle pressure fluctuates. The global atmosphere becomes clogged with volcanic ash, lowering temperatures further in some regions while greenhouse gases spike temperatures in others. The climate becomes a war zone, fought between fire and ice. All of this is happening while the black hole remains largely unseen. It does not glow. It does not roar. It merely pulls, subtly, relentlessly, distorting the geometry of space itself around Earth. To astronomers, this influence appears not only in orbital anomalies, but in the subtle bending of starlight near the horizon, gravitational lensing now visible to the naked eye on certain nights. The stars no longer twinkle the way they used to. Some double. Others curve. The sky seems wrong. Foreign. Alien. Human civilization, still trying to comprehend what is happening, begins to fracture. Entire nations collapse under the weight of agricultural failure, coastal displacement, and resource wars. Satellites drift off course, GPS systems fail, and international communication begins to deteriorate. People cling to outdated calendars and clocks, but reality no longer adheres to our measurements. What does a year mean when Earth's orbit has shifted by millions of kilometers? And then comes a darker question: will Earth remain bound to the Sun at all? If the black hole passes close enough or stays long enough, Earth may be gravitationally slingshot out of the solar system altogether. The Sun's gravitational dominance, once enough to bind Earth eternally, is now under siege. With each passing day, the black hole's competing gravity stretches that bond thinner. If Earth is ejected, it would become a rogue planet, cast into the freezing darkness of interstellar space. Without sunlight, temperatures would plummet to hundreds of degrees below zero. The atmosphere would condense and freeze. Life on the surface would end almost immediately. Only those deep underground, or in high-tech bunkers or space stations, might survive. But ejection is only one possibility. The other is far more terrifying. If the black hole continues its inward trajectory, Earth's elongated orbit may gradually decay, not away from the Sun, but toward the event horizon. In this scenario, Earth wouldn't freeze, it would burn. Pulled ever closer to the black hole, our planet would be subjected to increasingly violent tidal forces. Mountains would flatten. Oceans would boil. The crust would crack. And eventually, Earth itself would be torn apart into a spiral of incandescent debris, drawn into the singularity like thread into a needle. In either case, ejection or absorption, the distortion of Earth's orbit is the beginning of the end. The solar system is collapsing, and Earth's place within it is no longer secure. What was once a haven of stability, balance, and life has become a trembling raft adrift in a cosmic whirlpool. And the black hole, that silent invader from the void, draws ever closer. At first, it's subtle, so subtle that most people wouldn't even notice. The moon seems a little distorted. Stars near the horizon appear slightly curved, like light bending through a wineglass. A few amateur astronomers take photos, noting out elongations in the shape of constellations. They share their findings online, but at first, they're dismissed as lens flares, atmospheric distortions, or camera malfunctions. But soon, the evidence becomes undeniable. The sky is changing, not in color, not in brightness, but in geometry. This is the age of gravitational lensing. As the black hole encroaches ever closer to the inner solar system, it begins to warp not just matter and orbits, but light itself. Its immense gravitational pull curves spacetime, and as a result, it bends the paths that photons take on their journey from distant stars to Earth. This distortion creates a surreal, alien effect. Familiar constellations become warped and twisted. Some stars appear doubled or smeared. Others vanish from sight, hidden behind the bending of space. On the clearest of nights, away from light pollution, the sky once provided a canvas of order. The constellations, Orion, Ursa Major, Scorpius, were predictable, comforting, ancient. But now, they seem to shift unnaturally. Betelgeuse elongates. Sirius blurs. The stars near the ecliptic begin to look as though they're rippling, like reflections on water. What you see is not where the star truly is. Light is being funneled along curved paths, creating a mirage of cosmic proportions. The moon, too, begins to behave strangely. It's still there, orbiting Earth, but under the influence of the black hole's gravitational field, its apparent position in the sky becomes erratic. At times, it appears unnaturally large, magnified by the curvature of space itself. On other nights, it seems to jump slightly from one position to another, confusing even veteran skywatchers. And then comes the impossible, lunar mirages. A second ghostly image of the moon, hovering nearby in the sky, a product of gravitational lensing duplicating its light path. It's not a reflection, not a trick of the eye, it's a gravitational illusion. Solar and lunar eclipses, once forecast with precision centuries in advance, now fail to align. The moon's orbit, disturbed by both Earth's distorted path and the pull of the black hole, becomes irregular. Eclipses arrive early, or not at all. Shadow paths change mid-transit. The ancient alignment between Earth, Moon, and Sun begins to break down. And during a solar eclipse, something even more uncanny begins to emerge, a shimmering ring, not of the Sun's corona, but of warped starlight surrounding an invisible void. The black hole itself, now closer than ever, begins to lens the background of the universe. The area of sky near the black hole becomes the most bizarre of all. To the unaided eye, it still appears as empty darkness, no visible object, no glowing disk. But the stars behind it swirl and stretch, forming strange arcs and glowing rings. This is known as an Einstein ring, a perfect circle of light created when a massive object warps light from behind it into a full loop. Telescopes capture these ghostly halos, and for the first time, the location of the black hole is visible, not through its own emissions, but through the lensing of everything behind it. In that region of sky, nothing behaves normally. Time itself slows. Light bends. Radio waves delay. Space seems to breathe and shimmer with a strange energy, as if reality itself is weakening. The Milky Way, once a familiar band of light across the sky, begins to fracture. Its dense core appears smeared. The galactic plane bends in odd ways, especially near the black hole's lensing field. In dark regions far from cities, the night sky no longer provides guidance, it's a canvas of distortion. Some stars become magnified and flicker like dying embers. Others stretch into streaks. Comets moving through the sky leave tails that curve bizarrely, not just due to solar wind, but from the bending of space itself. Human reactions range from awe to existential dread. For millennia, people have looked up at the sky for stability. Sailors navigated by the stars. Farmers planted by the moon. Cultures told stories through the constellations. But now, the sky has become unstable. Unknowable. Scientists scramble to track the distortion's progress. Astronomers develop new predictive models that account for curved light paths, but the models collapse every few weeks as the black hole continues to move inward, warping space more aggressively. And then, there are new optical phenomena. For the first time, humanity sees photon spheres, ribbons of light trapped briefly in orbit around the black hole, then released in random directions. These pulses of light shoot across the sky at odd angles, blinking in and out of existence like flashes from a broken strobe. Some are visible as brief streaks of white or blue, others appear in infrared or radio frequencies. These are not shooting stars. These are trapped beams of light, whipped around the black hole and flung across the cosmos. The sun, too, begins to show subtle signs of distortion. At dawn and dusk, its shape seems slightly off, not a clean disk, but a wavering ellipse, as photons skim near the edge of the black hole's gravity well. Sunrises are delayed, sunsets arrive early, not because of Earth's rotation, but because of the time delay and curvature imposed by the nearby singularity. The very notion of where something is in the sky loses meaning. In a universe with flat space, position is predictable. But near a black hole, even location is a function of warping. Astronomers begin referring to apparent positions and true paths as separate concepts, and the distance between them grows by the day. Eventually, the sky begins to resemble an alien planet. Not because new stars appear, but because the old ones can no longer be trusted. A sky of loops, arcs, doubles, distortions, and missing points. A sky where familiar patterns have been erased or twisted into monstrous new shapes. And all of it, a direct result of that silent visitor. The black hole never emits light. It never makes a sound. But it warps the entire backdrop of the universe simply by existing. The Earth, still orbiting in a crooked dance between the sun and the void, continues to fall deeper into the storm. The stars no longer tell us where we are. The night has become strange. And it's only going to get stranger. It begins deep beneath our feet. The surface of Earth, though it seems solid and immovable, is nothing more than a floating crust, a thin, fractured skin over a roiling, molten interior. Our continents drift on tectonic plates, which glide slowly over the astrosphere, shifting at the pace of fingernail growth. But this delicate balance, held in check by Earth's gravity and internal heat, is about to be shattered by the tidal forces of a black hole, a cosmic stressor unlike anything this planet has ever experienced. As the black hole continues its slow encroachment upon the inner solar system, its gravity no longer acts merely on orbital paths or the light of distant stars. It now pulls directly on Earth itself. Like the moon once did, raising the tides, causing subtle shifts in the mantle, and guiding the rhythm of oceans, the black hole begins to exert its own gravitational grip. But unlike the moon's gentle tug, this is a force of titanic violence, stretching and squeezing Earth in ways our planet is not built to endure. The result is a new geological age. One not shaped over millions of years, but over weeks, days, and hours. The first to respond are the oceans. Earth's tides have always been dictated by a complex dance between the moon, the sun, and Earth's rotation. But now, a third actor enters the stage, a black hole with gravitational mass millions of times stronger than the moon's. The tides begin to rise higher than ever recorded. Coastlines vanish beneath walls of water. Entire cities flood not once, but twice or 3 times a day, as super tides whip around the planet, carried by the combined gravitational pull of 2 opposing forces, the sun and the black hole. In some regions, the oceans recede suddenly, exposing seabeds for miles before rushing back with unstoppable speed in tsunamis that make historical disasters look tame. Shipping routes are destroyed. Harbors vanish. Saltwater floods freshwater aquifers. Marine life, unable to cope with the rapid fluctuation of ocean levels, begins to die off in massive numbers. Coral reefs bleach and crumble. Fisheries collapse. Ecosystems built over eons are torn down in mere weeks. But the real horror is not above sea level, it's what's happening deep underground. As Earth's shape is distorted by tidal forces, pressure builds between tectonic plates. Areas where plates have long been locked together, held still by friction, waiting for the right trigger, now begin to slip. Earthquakes erupt across fault lines around the world in rapid succession. The Pacific Ring of Fire, that volatile belt of seismic and volcanic activity circling the ocean, begins to light up like a fuse. California's San Andreas Fault. Japan's Nankai Trough. Turkey's North Anatolian Fault. All begin to rupture. Some of these quakes are shallow and deadly, shattering cities, toppling infrastructure, and killing thousands. Others are deep megathrusts, quakes that displace entire slabs of Earth's crust, shifting coastlines by meters in a matter of seconds. Ancient fault lines, long dormant, awaken. Quakes begin to strike regions unprepared, regions with no seismic history. The Amazon Basin, Central Africa, the heart of Europe. Nowhere is safe. The crust itself begins to ripple and flex. Mountains begin to rise or sink in response to subterranean shifts. Fissures open in the ground, swallowing roads, buildings, and forests. Landslides and mudslides become frequent. The ground no longer feels stable, because it isn't. Volcanic activity follows closely behind. As the black hole's gravitational tug flexes the planet's interior, the magma chambers beneath dormant volcanoes begin to churn. Pressure builds beneath plugs of rock that once held back disaster. Now those plugs begin to crack. Geysers erupt in places never known for geothermal activity. Steam and ash shoot into the sky, grounding flights and choking the atmosphere. Then, volcanoes begin to blow. Mount Etna, Kilauea, Sakurajima, and Nyiragongo erupt with ferocity. Lava flows consume everything in their path. Ash clouds blot out the sun over entire continents, triggering global cooling. But these are only the preludes. The world watches in terror as supervolcanoes, geological time bombs like Yellowstone in the United States, Toba in Indonesia, and Campi Flegrei in Italy, begin to rumble. If even one of these giants erupts, the consequences are apocalyptic. Ash would rain over the globe, smothering crops, causing respiratory collapse, and dropping temperatures worldwide. Photosynthesis would grind to a halt. A volcanic winter would follow, months or even years of darkness, famine, and cold. With food supplies already stretched by climate disruption and flooding, humanity would face a new threat: starvation on a global scale. But the black hole's pull doesn't only affect Earth from the outside. Its gravitational influence stirs the core itself. The liquid iron outer core, which generates Earth's magnetic field through convection and rotation, begins to experience irregular flows. The magnetic field weakens, wavers, and perhaps even begins to collapse. Satellites begin to fail. Radiation levels rise. Auroras flicker not just near the poles, but across equatorial skies. Without a stable magnetic shield, Earth becomes vulnerable to solar winds and cosmic rays, just as space weather begins to spike due to the chaos unfolding across the solar system. Communication systems fall apart. GPS becomes unreliable. Power grids collapse under geomagnetic stress. The global infrastructure, built on assumptions of geological and electromagnetic stability, begins to fragment. And still, the Earth continues to shake. Every region, every continent, every ocean basin feels it. The black hole doesn't care about geography. Its tidal strain wraps around the entire globe, stretching the lithosphere, pressurizing the mantle, agitating the core. Earthquakes, once rare, now strike daily. Tsunamis cross oceans multiple times a week. Volcanoes, once sleeping, are now eternal fountains of fire. For humanity, the impact is devastating. The planet is no longer the same Earth it once was. And yet, the black hole still hasn't arrived in full. These disasters, these earthquakes, supertides, and volcanic surges, are just symptoms of its slow, methodical approach. It hasn't touched us directly. It hasn't swallowed us whole. Not yet. But it's coming. And every tremor, every flood, every plume of ash is a warning. A countdown, ticking closer to zero. Above the chaos on Earth, above the supertides, earthquakes, and volcanic infernos, the moon still circles, faithful and familiar. To the average observer, it may even seem like the last steady presence in a world unraveling. Its soft glow still washes over the night sky, casting silvery light on a planet now twisted by gravitational violence. But that light is growing uncertain. The moon, too, is caught in the cosmic struggle, and its fate may be the next to turn tragic. The moon has always been more than just a companion. It stabilizes Earth's axial tilt, governs our tides, and shapes the rhythm of life on the planet. Without it, Earth would wobble chaotically, seasons would fluctuate wildly, and the very foundations of biological cycles would collapse. But as the black hole moves ever closer to the inner solar system, its gravity begins to challenge the delicate gravitational bond between Earth and its moon. That bond has held for over 4 billion years. The moon orbits Earth at an average distance of about 384,000 kilometers, locked in a careful balance between Earth's gravitational pull and the moon's orbital momentum. But now, there is a third actor entering the equation, the black hole. And it doesn't play by the same rules. At first, its influence on the moon is subtle. Orbital perturbations, irregular tidal bulges, slight deviations from the path predicted by even the most advanced lunar models. But these small distortions soon become wild oscillations. The moon begins to drift farther away in some parts of its orbit and closer in others. Its once predictable path around Earth becomes a shaky ellipse. The dance becomes unstable. Tidal interactions intensify. Earth and the Moon begin exchanging angular momentum at unpredictable rates. The Moon's orbit stretches. Its speed fluctuates. Sometimes it gains momentum, sometimes it lags. But more terrifying than orbital drift is the prospect of gravitational capture, the black hole reaching out and pulling the Moon directly into its own sphere of influence. If the black hole's gravitational well overlaps with the Moon's orbital path, there are a few possible, and terrifying, outcomes. 1. The black hole steals the Moon. This event, known as gravitational stripping, would begin slowly. The Moon would start to spiral outward, no longer solely bound by Earth's gravity. Earth's pull would weaken just enough, and the Moon would begin to drift. Over weeks or months, it would elongate its orbit, heading away from Earth, toward the distant black void. People on the ground would watch as the Moon climbs higher in the sky each night, then begins to lag behind. Its face might appear slightly different, the orbit now tilted, the angle unfamiliar. Eventually, it would no longer follow a closed loop around Earth, but a chaotic spiral, each night's position more unpredictable than the last. Then, the Moon would vanish, swept into a new orbit around the black hole, or worse, falling directly toward the event horizon. In this scenario, the last glimpses of the Moon would be heartbreaking. It would shrink in the sky, dimming gradually. Then, a final moment of brilliance. As it crosses the black hole's photon sphere, gravitational lensing would bend the light from its surface, creating a haunting halo, a ghostly ring of moonlight around a hole of perfect darkness. Then, silence. Gone. No explosion. No warning. Just absence. 2. The Moon is torn apart before it ever reaches the black hole. This is perhaps even worse. As the black hole's tidal forces grow stronger than the gravitational cohesion holding the Moon together, the satellite would be ripped into pieces in an event known as tidal disruption. The far side of the Moon would be pulled faster than the near side, stretching the body like taffy. Cracks would spread across its surface. Lunar quakes, more powerful than anything previously recorded, would shake it apart. Chunks of the Moon would be drawn out into space. Some would spiral into the black hole. Others would fall toward Earth. What once illuminated our nights would become a deadly meteor storm. Moon fragments, each the size of cities or mountains, would slam into the atmosphere, igniting with unimaginable energy. A rain of destruction would fall, striking oceans, continents, and tectonic plates with the force of extinction-level impacts. The heat from these impacts would vaporize everything for hundreds of miles. Shockwaves would encircle the globe. Ash clouds would blot out the sun. The biosphere, already suffering from earthquakes and volcanic winter, would collapse under this final assault. 3. The Moon doesn't escape, but it no longer orbits Earth. Instead, the Moon becomes trapped in a chaotic resonance, no longer maintaining a stable distance or path. It oscillates unpredictably, sometimes coming far too close to Earth, raising tides hundreds of meters high, risking tidal locking failure, or even collision. If Earth and the Moon are driven together by gravitational chaos, the result would be nothing short of planetary annihilation. The collision of the Moon with Earth would release energy equivalent to 1 trillion nuclear bombs. Oceans would boil. The atmosphere would ignite. A new moon might form from the debris, eventually, but humanity, and all current life, would not survive the impact. And if none of these apocalyptic outcomes happen immediately, if somehow the Moon continues to orbit Earth for a time, its destabilized orbit would still wreak havoc. Its gravitational effect on the oceans would become unpredictable, causing tides to rise and fall without pattern. Whole cities would be washed away not by tsunamis or storms, but by the ordinary tides made monstrous. High tide would become extinction tide. Without the Moon's stabilizing influence, Earth's axial tilt could swing wildly, leading to climate chaos on a planetary scale. The poles could shift. The equator could tilt. Ice caps might melt while deserts freeze. Agriculture would fail. The calendar would lose meaning. Global seasons would turn into planetary roulette. And beyond all of this, there would be the sheer emotional and psychological weight of it. For as long as humans have existed, the moon has been a constant. It has inspired myths, guided sailors, marked time, and watched silently over the Earth every night. Its slow phases connected us to the cosmos. Its eclipses filled us with wonder. Its presence was an anchor in the void. To lose the moon, or watch it die, would be to lose a part of Earth's identity. It would sever a link to our past, to our planet's formation, to our ancient cultures, and to the very rhythm of our lives. And it would remind us, with cruel finality, that the black hole is not merely a visitor. It is a destroyer. It doesn't shout, it doesn't glow. It erases. It takes. And now, it may take the moon. One more piece of Earth, stolen by the void. Until now, the sun has stood defiant. Our star, ancient, radiant, and unimaginably massive, has remained at the center of the solar system for over 4.6 billion years. It commands the orbits of planets, powers all life on Earth, and bends space-time with a gravitational presence that anchors everything in its grasp. But the black hole, that silent monster from the void, is now close enough to threaten even the sun. Though a black hole may still be far from the sun in terms of direct contact, it doesn't need to touch the star to disrupt it. Its gravity, like an unseen blade, begins to interact with the sun's own gravitational field, pulling and twisting space around it. At first, these interactions are minor, subtle. But soon, solar scientists begin to notice something strange. The sun is changing shape. Normally, the sun maintains a nearly perfect sphere due to the balance between gravitational compression and the outward push of nuclear fusion at its core. But with the black hole's immense gravitational presence distorting nearby spacetime, that balance begins to falter. The outer layers of the sun start to bulge slightly toward the black hole's direction. What was once a uniform sphere becomes oblate, stretched along the axis pointing toward the cosmic intruder. This distortion isn't just physical, it's magnetic. The sun's magnetic field is an ever-shifting, complex structure powered by the movement of plasma within its convection zone. These magnetic fields give rise to sunspots, solar flares, and coronal mass ejections. But now, under the influence of an external gravitational force, the movement of plasma begins to change. The carefully choreographed dance of charged particles becomes more erratic, disrupted by the warping of the space through which they travel. Solar flares become more frequent and more violent. Some reach Earth and other inner planets with incredible intensity, unleashing torrents of radiation and charged particles. These solar storms rip through magnetospheres, fry satellites, and trigger power grid failures. Earth's sky lights up with auroras not just at the poles, but at the equator, as the planet's weakened magnetic shield struggles to contain the onslaught. But the real danger comes from coronal mass ejections, giant eruptions of plasma and magnetic field from the sun's outer atmosphere. The black hole's presence seems to trigger these events like a gravitational drumbeat. Each ejection becomes more massive than the last, hurling billions of tons of solar material across space. Some of these are aimed directly at Earth. If one of sufficient strength connects, it could cause a global technological blackout, permanently damaging transformers, disabling GPS, and plunging modern civilization into darkness. Yet the solar magnetic field doesn't just grow erratic, it begins to fragment. Normally, the sun undergoes an 11-year solar cycle, where magnetic poles flip and sunspot activity waxes and wanes in predictable patterns. But under the gravitational stress of the black hole, this cycle breaks down. Magnetic loops stretch unnaturally, connecting across hemispheres in ways never seen before. Some areas become magnetically hyperactive, while others go dead. The solar corona, the sun's superheated outer atmosphere, flares with enormous energy, heating to tens of millions of degrees. At the same time, helioseismology, the study of waves moving through the sun's body, reveals strange anomalies. Waves traveling through the sun begin to scatter, interfere, or vanish entirely. It's as if something is disrupting the sun from the inside out. Some theories suggest the black hole is triggering turbulence in the sun's core, disturbing the nuclear fusion reactions that power it. The implications are staggering. If fusion rates fluctuate, even slightly, the Sun's energy output could vary unpredictably. This would lead to temporary increases or decreases in solar luminosity. Earth, already dealing with orbital distortion and gravitational chaos, would now face another variable, solar flux. Days of blistering heat may be followed by sudden drops in solar radiation, freezing entire regions in freak cold snaps. Climate patterns would veer into unprecedented chaos. Crops would fail not just from seismic or tidal disaster, but from unreliable sunlight itself. And there is a more terrifying possibility, a solar instability cascade. If the black hole's proximity crosses a critical threshold, it could begin drawing material from the outer layers of the Sun through a process called gravitational stripping. Though unlikely unless the black hole passes extraordinarily close, if this begins, the Sun would start to shed plasma toward the black hole, forming a solar accretion stream. A delicate filament of solar matter would stretch through space, spiraling toward the darkness like a glowing umbilical cord. This would change the visual identity of the solar system forever. Instead of a clear separation between star and space, a luminous arc would bridge the Sun and the black hole, a blazing, twisted river of gas leaking across the void. The black hole, still invisible at its core, would begin to glow faintly with X-rays and gamma rays as it devours the material, producing a horrifying mockery of a second star. But this star does not give life. It takes. Solar mass loss of this magnitude could collapse the Sun's gravitational hold on the planets, accelerating the orbital decay already in progress. Mercury, Venus, Earth, and Mars might all be ejected or pulled into fatal orbits. The Sun itself might begin to dim, aging prematurely under the stress. Even if mass transfer doesn't occur, the solar wind, the constant stream of charged particles flowing from the Sun, becomes more chaotic, more powerful. It carves deep into planetary atmospheres, especially for those without magnetic protection. Mars loses the remnants of its already thin atmosphere. Mercury is scorched bare. Venus, with its thick clouds, becomes an oven of radioactive storms. Earth's own atmosphere begins to thin at the edges, losing its outer layers to space, one molecule at a time. Meanwhile, the visual effects in our sky intensify. Solar prominences, giant loops of plasma, now twist into bizarre spirals. The corona glows more intensely. Sunlight begins to arrive bent and delayed, distorted by the black hole's influence. Light flickers strangely, casting duplicate shadows on Earth, confusing animal behavior and disrupting biological rhythms. The Sun, once a symbol of constancy and life, now begins to feel unstable. Treacherous. Alien. And for the first time in the history of the solar system, it is not the central force. The black hole, though smaller in size, is rapidly becoming the dominant gravitational presence. It does not burn. It does not shine. But its influence is now unmistakable. The Sun is under siege. And the rest of the solar system will soon follow. The solar system, once a masterpiece of gravitational harmony, is now a battlefield, a cosmic tug-of-war between two colossal forces. On one side, the Sun, the ancient anchor of all planetary orbits, burns with nuclear fury, still trying to hold its family together. On the other, the black hole, invisible and relentless, pulls like a predator reeling in its prey. And in the middle of this terrifying struggle hangs Earth, caught between two titans, pulled in opposing directions, its fate uncertain. This gravitational conflict doesn't unfold with explosions or bursts of light. It's silent, subtle, slow. But it's more destructive than anything humanity has ever faced. The black hole's influence has grown to the point where its gravitational pull on Earth is measurable. It rivals, and in some regions of Earth's orbit, exceeds the Sun's own hold. That balance, the careful gravitational tether that has kept Earth at just the right distance from the Sun for billions of years, is now compromised. Earth begins to drift. Not in a smooth spiral, but in a chaotic wobble, as its orbit becomes contested territory. We are no longer just orbiting the Sun. We are now orbiting the interaction between the Sun and the black hole, a complex, dynamically shifting system. Earth is suspended in a gravitational tug-of-war, pulled first one way, then another, like a pendulum losing its rhythm. At first, these shifts seem astronomical, abstract calculations and data streams. But the consequences are physical. Tectonic. Lethal. When the sun pulls harder, Earth snaps closer to its heat, triggering waves of drought, atmospheric pressure changes, and dangerous ultraviolet radiation surges. When the black hole gains advantage, Earth slingshots outward, cooling suddenly, exposing itself to deep space radiation, and altering its entire orbital period. These shifts affect the length of the year. Some years become shorter, others longer. Earth's seasons stretch unpredictably. A summer that once lasted 3 months might now dominate half the year, while winter creeps across regions for 10 months straight. The global calendar disintegrates. Farming becomes impossible. Traditional timekeeping is rendered meaningless. Humanity begins living in a world without reliable days or seasons. But the most violent effects are felt in the planet's internal structure. Every slight change in orbital distance creates a shift in centrifugal force, and that difference is absorbed by the Earth's crust and mantle. The result: earthquakes increase exponentially. The Earth's tectonic plates are being tugged back and forth, cracking under stress. Previously unknown fault lines rupture. New mountain ranges begin to form in places that were once flat. Islands sink. Volcanoes, already awakened by tidal disruption, begin erupting in unpredictable waves, as mantle pressure builds and releases with every gravitational pulse. The oceans, too, are not spared. Each gravitational swing sends tides rolling in massive waves across continents. Entire coastlines are lost, then reformed. Water levels rise, fall, then rise again, as Earth swings between the sun and the black hole, unable to find a stable gravitational home. These aren't ordinary tides. These are continent-engulfing floods, capable of erasing civilizations in a single surge. Atmospheric chaos follows close behind. The jet streams shift erratically. Superstorms, driven by temperature contrasts from orbital shifts, become permanent features. Some regions are locked in endless hurricanes, others in polar vortexes that never retreat. The once stable climate zones, equatorial tropics, temperate belts, polar cold, dissolve into a churning mosaic of extremes. Humanity can no longer predict the weather, let alone survive it. Satellites in Earth's orbit begin to fail. Their carefully calculated trajectories are thrown off by the irregular pull of two gravitational centers. Communications collapse. GPS ceases to function. Military, scientific, and civilian technologies fall into silence. The night sky fills with streaks of falling satellites, burning up in a chaotic descent. Meanwhile, the moon, if it hasn't already been captured or destroyed, begins to behave like a traitorous wanderer. Its orbit destabilizes further. It moves erratically in the sky. On some nights, it rises at noon, on others, it doesn't rise at all. Its gravitational pull, no longer consistent, causes wild tidal irregularities. Earth's axial tilt, unmoored from the moon's stabilizing influence, begins to press us wildly, perhaps by dozens of degrees. This leads to the horrifying possibility of pole flips, the equator becoming the poles becoming tropical. The planet tilts, and tilts again, in desperate attempts to stabilize, but it no longer can. The biological cost is immeasurable. Flora and fauna, evolved over eons to operate on regular light cycles and seasonal cues, begin to fail. Crops do not germinate properly. Animal migrations falter and collapse. Hibernating species wake too soon or too late. Coral reefs bleach, recover briefly, then die again under cycles of heat and cold. Entire ecosystems collapse, not in years, but in weeks. Human infrastructure disintegrates. Roads crack under seismic activity. Bridges twist with tidal stresses. Power plants flood, then dry, then flood again. Water supplies become undrinkable. The supply chain ends not with war, but with chaos. Nations can no longer feed or govern their people. Global civilization breaks into isolated remnants, each facing a different flavor of apocalypse: flood, fire, frost, or quake. And still, the forces pulling Earth in opposite directions grow stronger. There is no escape. No refuge. No negotiation. Earth is not a player in this fight. It is a victim. The Sun, once all-powerful in our solar system, now struggles to retain its children. The black hole, with no desire, no intention, no malice, simply obeys physics. It pulls. Constantly. Unstoppably. As Earth continues to oscillate between these two giants, it begins to lose more than stability. It begins to lose mass. Yes, the planet itself starts to stretch. This is no longer just about orbital instability or magnetic collapse. Earth's shape begins to deform. Slightly at first, but then more rapidly. The black hole's tidal forces pull on the near and far sides of Earth differently, stretching it, elongating it, and pushing it past its physical tolerance. The Earth groans. Seams open along tectonic boundaries. Lava begins to pour from places that never had volcanic activity. The atmosphere thickens in some places, thins in others. Gravity becomes slightly weaker in some regions, stronger in others. People begin to notice the impossible, that dropped objects fall faster in one direction than another. That walking uphill now requires slightly more effort than the day before. These are signs of structural failure. The core of the Earth, that dense, spinning dynamo, may no longer be centered. It may be drifting under the influence of uneven external pulls. This imbalance could create vast new magnetic anomalies, or perhaps accelerate the collapse of the magnetic field altogether. And if Earth passes too close to the black hole in one of its chaotic swings, if it enters the region where the difference in gravitational pull between one side and the other exceeds the planet's structural integrity, the process of spaghettification could begin. The planet would be stretched, not instantly torn apart, but deformed slowly, horrifically. Oceans would run toward the black hole. The atmosphere would be stripped away. The surface would peel like layers of fruit, leaving only molten rock and core remnants, spiraling into darkness. This is the true horror of a gravitational battle between two giants. There is no mercy. No surrender. No middle ground. There is only force, and the price it demands from anything caught in between. The solar system, once a delicate cosmic clockwork of balance and stability, has become a minefield of unstable trajectories, decaying orbits, and celestial chaos. As the gravitational landscape warps under the dueling forces of the Sun and the approaching black hole, the neat, orderly paths of the planets begin to shift into madness. No longer locked in reliable ellipses, they begin to weave through space like drunken dancers, pulled and flung by forces too great for even their vast masses to resist. Each planet, once secure in its orbital lane, is now in danger of crossing paths with another. The mathematical probabilities that once made planetary collisions vanishingly rare are rewritten by the black hole's arrival. Under such gravitational stress, planetary collisions, a fate once reserved only for the earliest violent days of the solar system, become a looming reality once more. It starts subtly. Orbital resonance breaks down. Planets that once stabilized each other through gravitational interactions now lose those synchronizing patterns. Jupiter's protective role as the solar system's vacuum cleaner, absorbing or deflecting incoming comets, is disrupted. Its orbit begins to wobble. Its immense mass, no longer held perfectly in place, begins to tug violently on its neighbors. Saturn, just beyond, starts to drift inward. Now the gas giants are no longer passive giants peacefully spinning in the dark. They become weapons, massive, uncontrollable hammers moving at tens of kilometers per second, capable of annihilating anything they strike. If Saturn's orbit intersects Jupiter's, their collision would release a cataclysmic amount of energy. The impact would not be a fiery explosion, it would be a planetary-scale shockwave. Clouds of hydrogen, helium, and metallic gases would erupt into space, lighting up the system in a brief nova-like glow before settling into an expanding sphere of debris. If such a collision were to occur, the fallout would be devastating for everything else. Shockwaves of gravitational instability would ripple outward, pushing the inner planets, Mercury, Venus, Earth, and Mars, into new and unpredictable orbits. Each would face three possible fates: ejection, collision, or consumption. Some might be flung out of the solar system entirely. This is not merely theoretical. The black hole's pull acts like a slingshot. Planets that pass near its sphere of influence can be accelerated to such high velocities that they escape the sun's gravity entirely. These rogue planets would be launched into interstellar space, frozen, sunless worlds doomed to wander alone forever. Earth itself could face this fate, hurled into the void, stripped of its atmosphere, its oceans flash frozen, its surface locked in eternal night. But just as easily, the black hole could alter orbits in the other direction, sending planets hurtling inward, toward the sun. Venus, already on an unstable path, might spiral into the solar furnace, igniting in one final blaze. Mercury, being closest, might be the first to fall, skimming the sun's atmosphere in a spectacular death dive. Its crust would vaporize, its core boil, and the planet would disintegrate as it plunged into the sun's searing depths. Even Earth might follow, its path no longer elliptical but now hyperbolic, driving it into the sun on a collision course measured not in millennia but in weeks. Our atmosphere would boil away. The oceans would flash into steam. The crust would melt. The world would end not in ice or darkness, but in fire. Then there's the third possibility, planet-on-planet collision. Imagine Mars, its orbit wildly perturbed, now on a slow, terrible path that intersects with Earth's. Over months, the red planet grows brighter in the sky. Not as a light of hope, but a harbinger of death. As it approaches, Earth's gravity begins to interact with it, and tidal forces tear at both worlds before the final impact. A planetary collision isn't like two cars crashing. It's two entire worlds, each billions of tons of rock and metal, slamming together at tens of thousands of kilometers per hour. The collision would liquefy the crusts, vaporize the atmospheres, and hurl planet-sized fragments into space. The resulting debris could form a new ring system, or perhaps a new moon, but there would be no survivors. Life, civilization, history, it would all be erased in an instant. But even without direct collisions, the chaos continues. Some planets may begin to share overlapping orbital paths. In the past, these paths were safely out of phase. Now they may line up. As orbits decay, Venus might graze Earth's orbital trail. Mars might drift too close. Their gravitational interactions would further distort their motion, creating new risks of long-term encounters or near misses that evolve into collisions decades or centuries later. Meanwhile, the outer planets face their own apocalypse. Uranus and Neptune, destabilized by the collapse of the Kuiper Belt and the ejection of Pluto, could be thrown inward or outward. Their icy atmospheres, if they collide, would create titanic explosions, planetary fireballs seen across the system. Or worse, they might fall directly into the black hole itself, vanishing silently as their mass is consumed and converted into X-rays and gravitational waves. These collisions would send massive debris clouds spiraling through space. Asteroids, moons, and fragments of crust would become lethal projectiles. Some would rain down on surviving planets, bombarding surfaces with apocalyptic impacts. Earth, already reeling from quakes and tides, would now face planetary bombardment. Each collision would be more devastating than the one that killed the dinosaurs. There would be no hiding, no escape. Others' fragments would be captured by the black hole, spiraling into an accretion disk, a glowing, deadly halo of gas and rock, a final record of a solar system undone. And still, the black hole drifts closer. It is the catalyst of this entire collapse. It doesn't act with intent or malice. But its gravity rewrites the future of every planet, every moon, every rock in this system. The solar system is no longer a family of planets orbiting a life-giving star. It is a battlefield of giants. Each world now hurtles along a path of uncertain doom. Some will fall. Some will collide. Others may flee into eternal darkness. But none will remain untouched. It begins in eerie silence. No fireworks, no colossal explosion, no deafening roar. A planet, Mercury perhaps, or Mars, drifts too close to the black hole, crosses a cosmic line, and simply vanishes. One moment it's there, floating in the void like it always has, and in the next, it's not. It's as if the universe blinked and forgot it ever existed. This is the nature of the event horizon, the ultimate one-way boundary. Once anything passes this invisible threshold, not even light can escape. It's not a wall or a barrier you can see. It doesn't shimmer or glow. It is defined only by what it hides, the point of no return. The final silence. Now imagine Mercury, the smallest planet in the solar system, skimming the edge of the black hole's sphere of influence. It may begin as a gentle orbital decay. Perhaps a nudge from Venus, or an uneven gravitational tug caused by a destabilized sun, sends it off course. And then, gravity does the rest. As it nears the event horizon, a strange process begins. From the outside, an observer would see Mercury slow down, infinitely slow, as it approaches the edge. The planet would appear to hover on the brink, taking longer and longer to descend, its clock ticking more slowly in comparison to our own. This is gravitational time dilation. The closer Mercury gets to the event horizon, the more time slows down from our perspective. In fact, we would never see it fully cross. It would appear frozen on the edge of darkness, redshifted to the point of invisibility, dimming, fading, until even photons can no longer escape its fall. But from Mercury's point of view, if somehow it had sensors, instruments, a camera, it would be different. It would experience the fall as sudden and final. The pull would become overwhelming. Space would stretch. Time would warp. All directions would lead inward. There would be no turning back. Now scale that up to Mars. A world with polar ice caps, dust storms, canyons and valleys larger than Earth's. A planet that once may have held water, perhaps even life, plunging into the abyss. As Mars falls toward the event horizon, tidal forces begin to act. These are the different gravitational pulls on the near and far sides of the planet, tiny at first, but rapidly growing. The nearer side accelerates faster than the far side. Mars begins to stretch, to bend, to spaghettify. This isn't poetic exaggeration. It's physics. As the black hole's gravitational gradient becomes extreme, even the rock and iron core of Mars can no longer hold together. The planet would elongate like a stream of dough, pulled into a long, thin filament of dust and rubble. Its surface would crack. Atmosphere would shear away. Mountains would snap. Crust, mantle, and core would spiral inward in a twisted line of destruction, feeding the black hole bit by bit. Some of that matter wouldn't fall directly in. Instead, it would form a hot, glowing accretion disk, a swirl of gas, plasma, and fragmented debris, heating to millions of degrees as it spirals around the black hole. Though the black hole itself is invisible, this disk would shine. Mars's remains would light up the universe in X-rays and gamma rays as they die. For distant galaxies, it might look like a brief flash, a flicker in space where a planet once was. But the true terror comes with Jupiter. Unlike Mercury and Mars, Jupiter is a gas giant, massive, bloated, and brimming with hydrogen and helium. It's more than 300 times Earth's mass, and its gravitational pull is strong enough to have shaped much of the solar system's structure. Jupiter's fall into the black hole would be a cataclysmic event, unlike anything the solar system has ever experienced. As it nears the event horizon, the outer layers of Jupiter, its clouds, storms, and massive atmospheric envelope, would begin to spiral off. Some of this material would be stripped by the black hole's intense tidal forces even before crossing the threshold. Whole bands of gas could be flung outward in twisted arcs, glowing with frictional heat as they interact with the black hole's surrounding disk. Then, as Jupiter's denser inner core follows, the true feeding begins. Jupiter's mass would cause the accretion disk to flare dramatically. This flare could momentarily rival the brightness of the entire galaxy. Telescopes across the universe would see it. X-ray observatories would light up with data. The death of a planet would become a cosmic beacon, a warning to any who dare approach the void. As Jupiter crosses the event horizon, its mass would add significantly to the black hole zone. If the black hole were a stellar mass object before, Jupiter's fall could tip it closer toward the intermediate category. Its event horizon would grow slightly, an invisible expansion in the darkness. But this moment has further consequences. As planets fall into the black hole, they feed it, yes, but they also destabilize everything else. Each loss of mass from the solar system, each shifting of orbital centers, creates new chaos for the remaining worlds. Jupiter's moons, over 90 of them, would become orphans, flung into new orbits, colliding with each other, or falling inward themselves. Some might be captured by the black hole. Others might hurtle toward the inner planets as massive projectiles. Imagine Ganymede, the largest moon in the solar system, larger than Mercury, on a new collision course with Earth. Or Europa, flung into the Sun. Each planetary fall increases the entropy of the system. The Sun loses more of its hold. The black hole gains. And the gravitational balance that once guided our planets across millions of years is replaced with total unpredictability. Eventually, the solar system may become a disk of death, planets spiraling inward one by one, consumed, erased, until only the black hole remains. No evidence. No memory. Just a dark sphere floating in silence. The solar system, once a masterpiece of balance, symmetry, and vastness, begins to shrink, not in size alone, but in structure, stability, and meaning. The planets that once traced elegant, predictable paths around the Sun are now gone or flung far from where they belong. Those that remain cling desperately to their orbits, but the old gravitational regime has been shattered. The grand celestial harmony has ended. A new era has begun, one of fragmentation, collapse, and gravitational chaos. The process doesn't happen in an instant. It's drawn out, a slow-motion disassembly of a clockwork that once governed everything from the tides on Earth to the migration of comets at the edge of the system. As the black hole consumes or displaces more mass, the gravitational equilibrium is disturbed at every level. The outer planets are the first to vanish, and with each departure, the center of mass for the solar system shifts slightly, like a tower losing blocks from its base. It starts to lean, then to wobble, then to fall. With the disappearance of Jupiter, Saturn, and perhaps even Uranus or Neptune, the once spacious orbits of these giants become empty, but their absence leaves behind violent gravitational echoes. Moons, asteroids, and dwarf planets that once depended on the presence of these gas giants to shape and protect their paths now find themselves unmoored. Without Jupiter's shielding gravity, the asteroid belt begins to unravel. Objects that once peacefully orbited between Mars and Jupiter are now being flung in every direction, some into the Sun, others toward the Earth, and some into the black hole's event horizon, joining the ever-growing accretion disk glowing faintly in the background. The Kuiper Belt has long since descended into madness. Pluto, Haumea, Makemake, and thousands of icy bodies that once lay beyond Neptune are gone, ejected, consumed, or shattered by tidal forces. Their debris forms a chaotic halo of icy bullets, some returning as incoming meteors toward the inner planets, others vanishing into the dark. And now, even the inner planets, those rocky bastions of solidity, are in disarray. If Mercury has already fallen, Venus soon follows. Its thick atmosphere is no match for the shifting gravity wells, and if it's not pulled into the black hole, it may spiral into the Sun, its greenhouse hellscape igniting in one final blaze before vanishing beneath the solar surface. Earth, at this point, is no longer orbiting in a stable path. Its position relative to the Sun and black hole is erratic, its journey more like a lurching spiral than a circle. The seasons are gone. The days vary in length by the hour. Earth may have been slingshot outward, or dragged closer to one of the twin titans, or stuck in a bizarre, unstable orbit that flings it around like a stone caught between whirlpools. Mars, perhaps still intact, is in no better shape. If it hasn't yet been consumed or ejected, its orbit is also corrupt. Its thin atmosphere, already fragile, is torn further apart by solar wind and gravitational strain. Its moons, Phobos and Deimos, begin spiraling away, or perhaps crashing down onto the Martian surface in catastrophic impacts. If Earth and Mars still exist, they may cross paths. They may collide. Or they may be driven so far apart that they become estranged wanderers in a solar system that no longer resembles its original self. The Sun, while still burning, is no longer the center of attention. Its gravitational dominance has been undermined. It may have begun drifting under the influence of the black hole, dragging its magnetic fields and radiation with it. It is no longer a still anchor, it is now a participant in the chaos, moving ever closer to the black hole, possibly starting to feed it. As more material, planets, asteroids, debris, falls in, the black hole grows in mass. With each gain, its event horizon expands. Its gravitational range stretches wider. The solar system's former borders begin to collapse inward, not because the space is shrinking, but because nothing stable remains to occupy it. Distances lose their meaning. Once, the journey from the Sun to Neptune was a vast 4.5 billion kilometers. Now, with Neptune gone and only a few battered, unstable worlds left behind, the solar system feels compact, claustrophobic, even. Everything has either fallen in, fled out, or been shattered into drifting clouds of debris. There are no longer distinct regions. The asteroid belt bleeds into the inner system. The remains of the Kuiper Belt swirl unpredictably through every orbit. The Oort Cloud, once a distant shell of icy relics, is now pouring inward in a deadly rain of comets, many on intercept courses with the inner planets, or the Sun itself. The black hole's gravity acts like a collapsing umbrella, drawing everything into a funnel, reducing the majestic sprawl of the solar system into a concentrated arena of destruction. And as more objects fall in, this collapse accelerates. The more mass the black hole gains, the more it pulls. The more it pulls, the faster the rest follows. Space itself bends more acutely now. Starlight that once arrived as steady points begins to twist, smear, and shift as gravitational lensing becomes more dramatic. The familiar constellations are gone, warped beyond recognition or blotted out by streams of gas and debris. Navigation is impossible. Orientation meaningless. You can no longer tell which direction is in or out. Everything leads inward. The solar system, from a great distance, no longer looks like a bright disk of planets circling a yellow star. It appears as a dim, distorted ring of dust and rubble spiraling into a small, dark spot, the black hole, nearly invisible, surrounded by the faint, ghostly glow of things that used to be. Once, our solar system stretched across billions of kilometers and played host to countless worlds, moons, rings, and fields of ice and rock. It held comets with 100,000-year orbits and planets whose revolutions took centuries. Now, it has become a graveyard, a funnel, a wound in the galaxy. What once expanded with elegance and order has now collapsed in on itself, reduced to a few scattered survivors waiting for their turn to fall, or flee, forever. The chaos introduced by the black hole's gravitational intrusion doesn't just pull planets inward, it also has the power to fling them outward. While most think of black holes as cosmic vacuum cleaners, swallowing everything in their path, the truth is far stranger and more complex. Their immense gravity doesn't just attract, it manipulates. It can twist trajectories, destabilize orbits, and, under just the right conditions, launch entire worlds out of star systems like stones from a cosmic slingshot. And in this nightmare scenario, Earth may not fall into the black hole. It may be ejected. To understand how, imagine the solar system as a mobile hanging from a ceiling, each planet a carefully balanced ornament, spinning in place due to the gentle but consistent pull of the Sun. Now imagine someone shoving a bowling ball into that mobile. Orbits wobble. Some objects fall inward. Others, thrown off balance, are flung outward with incredible speed. This is what happens when a black hole passes near a planetary system. The moment Earth's gravitational tether to the Sun is weakened, perhaps by the black hole's growing dominance, or by the ejection or collision of neighboring planets, our home world may begin drifting outward. Not slowly, not peacefully, but violently. Accelerated by the gravitational interplay between the Sun, the black hole, and the remaining massive bodies in the system, Earth could be launched on a hyperbolic escape trajectory. From the perspective of those watching from space, it would look like Earth was whipped around by a massive invisible hand and then hurled toward the edge of the solar system, picking up velocity with each kilometer it travels. And once Earth reaches escape velocity, not just from the Sun, but from the entire solar system, there's no turning back. We would become a rogue planet. This is not a poetic term. It's a real astronomical concept. Rogue planets are planets that drift through the galaxy, unbound to any star, wandering alone in the blackness between solar systems. Until now, such planets have been theoretical or extremely difficult to detect. But in this imagined future, Earth has joined their ranks. The transition wouldn't be gentle. As Earth exits the Sun's gravitational domain, sunlight would begin to fade. The days would grow dimmer, first slightly, then rapidly. Within weeks or months, depending on the speed of ejection, the Sun would shrink to a bright star in the sky, no longer the disk that warms our days. Temperatures would begin to drop. The atmosphere would respond violently. Weather systems would destabilize, trying to compensate for the loss of the central heating mechanism that has shaped Earth's climate for billions of years. The skies would darken permanently. What was once the sky, blue by day, starlit by night, would become a cold black dome, filled with unfamiliar stars. Aurorae might erupt across the planet as the magnetosphere flares in its last acts of protection, reacting to the shifting cosmic environment. But without solar wind, even those would fade. Temperatures would plunge to catastrophic lows. Within days of full ejection, most of the surface water would freeze. Oceans would form thick ice caps, kilometers deep. The atmosphere would begin to condense and fall as snow, then freeze solid. Wind would cease. Clouds would vanish. Rain would become a distant memory. The Earth would become encased in a deep, frozen shell, a planet-sized cryogenic tomb. Only the heat from Earth's molten core would remain. Volcanic activity might continue, and in deep-sea vents, if the oceans haven't frozen entirely, some extremophile organisms might persist. But the biosphere, as we know it, would collapse. Photosynthesis would end. Most plant life would die, followed by herbivores, then carnivores. Ecosystems would collapse like dominoes. Extinction would sweep the planet. The fate of humanity would hang on one razor-thin question: could we survive underground? Subterranean cities, powered by nuclear or geothermal energy, might serve as temporary sanctuaries. Governments, if they still exist, may activate planetary arc systems, giant self-contained vaults designed to house thousands in the event of nuclear war or global catastrophe. But this is no mere catastrophe. This is cosmic exile. These bunkers would now be humanity's last home, possibly forever. Could we navigate space? Could we build engines to change Earth's trajectory? Theoretically, yes, but realistically, probably not. Moving an entire planet would require a scale of engineering far beyond anything we've ever achieved. Some might attempt to launch smaller vessels, generation ships or cryopods, into space in hopes of reaching another star system. But space is vast, and most systems are many light years away. What about colonizing moons or other bodies as Earth is flung outward? That window would have already closed. The moment Earth begins accelerating away from the Sun, our chance to reach other nearby bodies, like Mars or Europa, is lost. We would be moving too fast, and they would be receding too quickly in the opposite direction. From the perspective of the solar system, Earth's ejection is just another data point in a growing list of catastrophic losses. Another planet gone. Another orbit erased. But from the perspective of its inhabitants, those few who survive, it becomes an existential moment. Not extinction, but isolation. The interstellar medium, the space between stars, is not empty. It's filled with radiation, rogue debris, magnetic fields, and dangerous particles. Over millions of years, Earth may encounter a rogue asteroid or drift too close to a supernova. It might be bombarded by cosmic rays without the protection of a nearby star's heliosphere. Over geological timescales, the planet may freeze so thoroughly that even the crust solidifies entirely. Eventually, the magnetic field may decay. The core may cool. And Earth will become a lifeless, frozen husk wandering the dark like a memory of what it once was. But what if, somewhere, someday, it is found? Perhaps by another civilization. Perhaps by humans who escaped in ships and eventually circled back. They might approach a dark, frozen sphere wrapped in kilometers of ice and darkness. Beneath the ice, they might discover ruins, cities long buried, oceans turned to stone, relics of a world that was once alive. They would not find Earth as it was. But they would find the echo. Proof that once, in a star system long destroyed, there was a blue planet that teemed with life, knowledge, and civilization. And that in the face of a black hole, it did not burn. It did not fall. It escaped. It is the most terrifying fate imaginable, not because it happens with fire and fury, but because it happens in silence, in slowness, in sheer inevitability. Earth, falling into a black hole. The idea seems almost poetic. Our planet, once a cradle of life, being drawn into the cold, infinite darkness. But poetry fades quickly when you consider the reality. The gravitational monster that is a black hole doesn't merely swallow. It stretches, warps, and erases. To fall into a black hole is not to pass through a door. It is to experience the absolute end of time, space, matter, and meaning. And in this imagined doomsday, Earth's final act has begun. It starts subtly. After orbiting in chaotic paths for weeks, months, or years, caught in a tug-of-war between the Sun and the black hole, Earth's fate is sealed. The Sun is losing. The black hole has already devoured other planets, stolen moons, shredded asteroid belts, and swallowed gas and dust to become larger, more powerful, and more inescapable. Now it's Earth's turn. Our planet begins its final descent. At first, the world still appears normal. The skies might look strange, perhaps filled with gravitational distortions, star trails bent into spirals, a black patch in the sky where no light escapes. But the real danger isn't visual, it's gravitational. As Earth draws nearer, tidal forces begin to take hold. The side of Earth closest to the black hole is pulled more strongly than the side farther away. This difference in force becomes extreme. At first, this creates subtle stress across the crust. Earthquakes become common. The ocean tides go haywire, crashing onto land and pulling back with tremendous violence. Entire coastlines are destroyed. Mountain ranges tremble. Volcanoes erupt unpredictably. But this is only the beginning. Soon, the difference in gravitational pull is so severe that the planet begins to stretch. This is the infamous process of spaghettification. It's not a metaphor. It's a real and mathematically predicted result of being pulled into a strong gravitational gradient. Imagine Earth being pulled like warm taffy, its mass elongated into a long, thin stream of atoms and dust. The planet would tear itself apart. The crust would shear. The core would fracture. The atmosphere would be ripped away first, drawn into a stream of ionized particles spiraling toward the event horizon. Then the oceans boiled, atomized, and scattered. Finally, the solid planet itself would begin to unravel. From far away, the destruction would look hauntingly beautiful. Earth wouldn't fall in like a marble dropping through a hole. It would stretch into a line, a comet-like trail of glowing debris, spiraling inward in slow, majestic arcs. This is because the black hole would likely be surrounded by an accretion disk, a ring of matter so hot it glows in X-rays. Earth's destruction would briefly add to this disk, making the black hole flare with radiation. But time begins to break down. For someone watching from a safe distance, Earth's descent would seem to slow. This is gravitational time dilation, one of the strangest consequences of general relativity. The stronger the gravitational field, the more slowly time passes relative to an outside observer. As Earth approaches the event horizon, time from an external point of view slows to a crawl. We would see Earth stretch and freeze, asymptotically nearing the event horizon but never fully disappearing. To the people on Earth, however, if any have somehow survived inside underground bunkers or deep ocean habitats, things look different. To them, time feels normal. The stars outside would begin to distort. Light would stretch, colors would shift. As they fall closer, light from the outside universe would become redshifted until it fades entirely. Communication with the outside world, if it still existed, would cease. Clocks would tick normally, but the rest of the universe would seem to speed up beyond comprehension. A second inside the black hole's influence could mean centuries or eons to those on the outside. Eventually, they would see the cosmic horizon approach, the point at which nothing can escape. And once crossed, there is no going back. Not for people. Not for signals. Not even for light. Crossing the event horizon would be painless, in a cruel twist of fate. No alarms go off. No sensations warn of doom. You simply cross into a realm where the outside universe is cut off forever. Time inside continues normally, at least for you, but your fate is sealed. From this point forward, all directions lead inward. Space and time flip roles. You cannot avoid the singularity. The singularity, the heart of the black hole, is not well understood. It is where gravity becomes infinite, and the known laws of physics collapse. Everything that enters is compressed into a single point of zero volume and infinite density. What happens to Earth's atoms, its elements, its history, its memories? Are they destroyed completely? Or encoded in some unknowable way into the black hole's mass, charge, and spin? Some theories suggest that information is not lost but stored on the black hole's surface, the event horizon, forever etched in quantum fluctuations. Others say it's gone for good. Regardless, Earth's fall ends in the singularity, crushed into nothingness, a once-living world reduced to mass energy in a place where time no longer flows. And what would such a fall feel like? Theoretically, if someone were falling in feet first, like an astronaut in free fall, they would experience a phenomenon known as vertical spaghettification. Their feet would be pulled faster than their head. Their body would stretch, atoms separating, molecules shredding. Nerves would break before they could send pain signals. Consciousness would end long before the plunge is complete. The body would become a line of atoms. The mind, extinguished. If Earth falls as a whole, the same thing happens, just on a planetary scale. Torn. Stretched. Consumed. Gone. And all of it would happen in absolute silence. There is no atmosphere inside a black hole, no medium for sound. Just the quiet annihilation of all that was. The noise, the life, the movement, it all vanishes. A blue world that once spun through the cosmos, alive with thought and motion, now reduced to mass and spin and nothing more. From the galaxy's point of view, nothing much has changed. The black hole grew slightly. A new ripple of gravitational waves spread outward, detectable, perhaps, by alien civilizations with advanced instruments. They might notice the loss. But they would not know what was lost. They would not know it was Earth. They would not know it was us. We would have entered the deepest shadow, the one from which nothing returns. Humanity, in the face of the greatest cosmic threat ever imagined, would be forced to confront a chilling truth. Survival may not be about fighting back, but about holding on. As the solar system collapses around us, as planets fall or flee, and as Earth itself spirals toward destruction or exile, the question becomes not how to save the world, but whether we, as a species, can find a way to survive without it. The first line of defense would not be military. It wouldn't be missiles or shields. It would be bunkers, space stations, and the last-minute deployment of humanity's deepest ingenuity. In the early days of the black hole's approach, as strange orbital shifts and cosmic signals begin to confirm the unthinkable, governments and scientific institutions around the globe would face a grim race against time. For the first time in history, every resource would be focused not on progress, not on war, but on preservation. Let's begin with the underground bunkers. It's the most accessible plan. Dig down, shield the population from the surface chaos, and wait out whatever happens above. Even today, deep Earth bunkers exist, designed to withstand nuclear war, asteroid impacts, or global pandemics. These facilities could be rapidly converted into life-supporting arcs. Massive drills would carve deeper shelters into tectonically stable regions. Entire cities might be replicated underground, complete with artificial lighting, hydroponic farms, geothermal heating, and radiation shielding. But how long could we last down there? If Earth is flung into deep space as a rogue planet, surface conditions would become uninhabitable in weeks. Temperatures would plummet, the atmosphere would begin freezing, and sunlight would fade into memory. Underground, with sufficient geothermal energy and nuclear reactors, humanity might survive for years, or even centuries, assuming food, water, and oxygen cycles are maintained. But these underground habitats would face increasing challenges. Mechanical failures. psychological strain, social unrest, generations born in darkness, and worst of all, isolation. Communication with space or Earth's surface would likely vanish. If the moon were pulled away or Earth's orbit destabilized, even the tides and magnetic field could go haywire, affecting everything from navigation to animal migration. Earthquakes triggered by gravitational strain could collapse tunnels. Supervolcanoes might erupt. The very ground in which we hide could become unstable. Eventually, survival in bunkers might not be enough. That leads us to the second possibility, space stations. If Earth is doomed, whether to be swallowed or slingshot, the only way to preserve civilization could be to leave it behind. Current space stations like the International Space Station are too small, too fragile, and not self-sufficient. But given enough warning, humanity might redirect all resources into building large orbital habitats, perhaps based on existing designs like O'Neill's cylinders or Stanford tori, gigantic rotating structures that simulate gravity and sustain life indefinitely. These artificial worlds could house thousands, maybe millions, provided we have the time to construct and launch them. They would be powered by solar arrays or compact fusion reactors. Water could be recycled. Food could be grown in zero-gravity gardens or vertical farms. But the logistics are immense. Launching enough mass into orbit, assembling it in hostile conditions, and transferring Earth's population into space and time. It's unlikely we'd move billions. More likely, space stations would be arks for survival, carrying a fraction of humanity, perhaps the most skilled engineers, doctors, scientists, and children, into orbit in hopes of outliving the solar cataclysm. But even this would not be enough if the black hole stays. Earth's orbit would become unpredictable. Satellites and stations would either fall into the black hole or be flung into the void. Only stations far enough away, or designed for long-term drift, might survive. Some would become lifeboats, drifting between the stars for decades or centuries, in search of rescue or refuge. And this leads to the final, most ambitious hope, escaping to another star. Interstellar travel has long been a dream. But faced with annihilation, it would become an imperative. Humanity would pour every ounce of remaining energy into building generation ships, vast starfaring vessels designed to carry human life across light years. These ships wouldn't travel at light speed. They'd move slowly, over centuries, carrying hundreds or thousands of people in cryogenic sleep or self-sustaining ecosystems. Where would they go? The nearest star system, Proxima Centauri, is over 4 light-years away. At current speeds, it would take 70,000 years to reach. But with advanced ion drives, fusion propulsion, or breakthroughs like the theoretical Alcubierre warp drive, we might make the journey in a human lifetime. The challenge wouldn't just be propulsion, it would be guidance, protection, and survival. Deep space is hostile. Radiation, cosmic dust, mechanical breakdowns, social and psychological isolation over generations. A single failure in water recycling or energy production could doom the mission. And even if they arrive, what would they find? An uninhabitable rock? Or perhaps a planet with the potential for life? If we're lucky, one of these ships might find a new home. A second Earth. A place to begin again. But it's also possible that we go silent. That humanity's last voice drifts alone through space, unheard, unrescued, forgotten. And still, we might try. Because even if Earth dies, even if the solar system unravels, the one force greater than a black hole is the will to survive. To build. To remember. To carry forward stories, songs, knowledge, even if only in one starship, one station, or one cave deep beneath a frozen mountain. In the end, survival wouldn't be about preserving our planet. It would be about preserving meaning. About deciding that life, consciousness, and the fragile miracle of human thought are worth saving, no matter how dark the future becomes. And perhaps, if we survive long enough, we might even one day return to the place where it all began. Could we stop it? Could humanity, armed with our science, our machines, our dreams, stand against the most terrifying force in the universe? Could we do anything to divert, delay, or defeat a black hole barreling into our solar system? It sounds like a question fit for science fiction. But in a universe where the unimaginable can suddenly become real, it's one we'd be forced to ask. And while the honest answer may be painful, it's also an invitation to stretch the limits of imagination, physics, and will. Let's first confront the blunt reality. A black hole is not just an object. It is gravity itself, condensed and weaponized. A singularity of mass so dense that space and time bend around it. You cannot touch it. You cannot break it. You cannot blast it apart, because there's nothing to blast. It has no surface. No crust. No heart. It's an abyss in space-time itself. If it has mass greater than a planet, a star, or even several suns, the energy needed to move it, to nudge it, would be unfathomably immense. And yet, if humanity had enough time, perhaps decades or even centuries of warning, would we try? Yes. We would. The first idea might be familiar: massive explosives. Could we throw our nuclear arsenal at it? In short, no. Nukes, even thousands of them, are pitiful against the gravity of a stellar mass black hole. The explosions would detonate and vanish into the void. They might illuminate the event horizon for a moment, but cause no harm. You can't destroy a hole. You can only avoid it, or try to steer it. So we move to more creative strategies. What if we could deflect the black hole? To change the course of something so massive, we would need to exert an equal and opposite force, a push. But how do you push a black hole? One hypothetical method involves the gravity tractor concept, scaled to absurd levels. We currently imagine gravity tractors as spacecraft that hover near an asteroid, using their own gravitational pull to gently alter the object's path over time. Could we build something massive enough, say, an entire fleet of spacecraft carrying dense matter or high-thrust engines, that hovers near the black hole and nudges it off course across decades? The problem? You need to match the black hole's speed and velocity to even stay near it, probably at relativistic speeds. And you need an object of comparable mass to exert any real influence. In other words, unless we have a second black hole, or an engineering project on the scale of a Dyson sphere, this option dies under its own weight. What about using electromagnetism? Black holes can carry an electric charge or spin at high rates. Could we manipulate their path with huge magnetic fields or charged plasma? Unfortunately, while magnetic fields can affect particles near a black hole, they can't push the black hole itself. It's not a spaceship. It doesn't respond to forces in that way. Plus, any artificial magnet powerful enough to influence a black hole would require godlike engineering, and energy on the order of several stars' outputs. But what about Hawking radiation? This theoretical radiation, proposed by Stephen Hawking, suggests that black holes evaporate slowly over time by emitting tiny amounts of energy. Could we accelerate this process? Could we starve or boil the black hole until it vanishes? In theory, yes, but in practice, no. Hawking radiation is mind-numbingly slow. A stellar mass black hole would take trillions of years to evaporate naturally. Even if we could somehow feed it exotic matter that accelerates the process, such as negative mass particles, which may not even exist, we'd be fighting against time in a war we've already lost. Still, some physicists have proposed feeding black holes matter in a precise way to create energy output from the accretion disk, effectively building a giant black hole engine. Could we harness that energy to power a defensive system? Or even to move the black hole itself? Again, the scale is immense. Even if we could build such a system, we'd have to approach the black hole, survive the tidal forces, insert matter at exact angles, and then somehow channel that energy. All before the black hole gets too close and consumes the machinery. There's another more radical concept. Create another black hole. The idea sounds insane, but if we could artificially generate a small, controlled black hole using high-energy collisions, far beyond anything the Large Hadron Collider can do, perhaps we could counterbalance the invading one. Use gravitational interference to neutralize, deflect, or absorb the incoming threat. But this carries risks no one is ready for. Two black holes converge, becoming a larger threat. Or they could dance in unpredictable orbits, flinging each other, and everything nearby, into chaos. Even setting the difficulties of creation aside, controlling such a collision is likely impossible with any foreseeable technology. So we look beyond technology, to hope in physics. Could we redirect the black hole by manipulating dark energy? Could we tap into exotic particles, quantum fields, or extra dimensions to open an escape route, a wormhole, perhaps, to cast it elsewhere? These ideas are deeply speculative. We don't yet understand dark energy well enough to use it, let alone weaponize it. And while wormholes are mathematically possible, they require negative energy, a substance we've never seen, and they may collapse before anything can pass through. So far, every road ends in futility. But does that mean there is nothing we can do? Not necessarily. Maybe we can't stop the black hole. But maybe we could move the solar system. A bold idea first proposed by astrophysicist Greg Laughlin and others: build gigantic thrusters, called Shkadov thrusters or stellar engines, around the Sun to slowly push the entire solar system away from danger. The idea would involve reflecting radiation from the Sun in one direction to create a small, continuous thrust. Over millions of years, this could shift the Sun's position in the galaxy, along with all its orbiting planets. Too slow for an incoming black hole? Likely. But if we had early detection, millions of years in advance, it could be a feasible long-term strategy for escaping danger zones in the galaxy. The true defense, then, is time. Time and foresight. Which leads to perhaps the most important idea of all. If we can't stop a black hole, we must detect it early. Telescopes that constantly monitor gravitational lensing, galactic drift, and stellar anomalies. AI systems trained to spot the faintest warp in star positions. Observatories watching for X-ray bursts, cosmic background ripples, and long-range orbital irregularities. The earlier we detect a rogue black hole, the more options we have. Prepare bunkers. Launch stations. Evacuate populations. Aim starships outward. In the end, maybe we don't stop the black hole. Maybe we just get out of its way. And if we do that, if we live to see another sunrise, even in another solar system, we will have one. Not by defeating the universe, but by refusing to give up. Imagine the horror and wonder of looking up into the sky, not to see a golden sun rising over the horizon, but a yawning shadow. No glowing warmth. No light-giving rays. Just darkness. Cold. Silence. The black hole has arrived, and it has taken the sun's place. This isn't merely the end of our sun. It's the erasure of everything the sun represented: light, warmth, gravity, stability, time. Now, at the heart of the solar system, where fusion once roared and solar flares danced into space, there is only a void, a black hole that has swallowed our star and taken its place. How could this happen? If the black hole were to pass close enough, it could slowly consume or destabilize the sun. If the masses are similar, a complex gravitational ballet might end with the sun falling inward, feeding the black hole's hunger until only the remnant remains. In the most extreme cases, a collision or merger could occur, tearing apart the sun in spectacular fashion, ejecting matter across space and leaving a black hole behind in its orbit. Alternatively, the black hole might not need to consume the sun completely. It could instead replace it by sheer gravitational dominance, taking over the central role in the system. If the sun is slingshot out of the system or collapses under stress, the black hole becomes the main gravitational anchor. What happens next is unlike anything life on Earth, or anywhere, has ever experienced. First, we must understand what this new sun would be. A stellar mass black hole would exert similar gravitational influence if its mass matches that of the sun. It could hold the planets in orbit, stabilizing them just as the sun once did. Gravity would remain, but that's all. There would be no fusion, no light, no solar wind, no warmth. From a distance, you might not even know it's there. No glowing sphere. Just the eerie absence of starlight. The planets would continue circling, caught in an invisible leash around a silent predator. But life, at least as we know it, would not survive. Without sunlight, photosynthesis ends immediately. Plants begin to wither. The food chain collapses. Temperatures plummet across the solar system. Within a week, Earth's average surface temperature drops below freezing. Within a year, it plunges to minus 70 degrees Celsius. The oceans begin to freeze from the top down. Within a few years, the planet is encased in thick ice. The atmosphere condenses and falls as frozen rain or snow. The sky, once blue, becomes crystal clear, no clouds, no haze, just blackness. The stars dominate the sky, steady and eternal, but the central beacon of light is gone. In its place, nothingness. But there is still a presence in the sky. Where the sun once was, a black region appears. Not darkness exactly, but a distortion. A warped bubble of space where stars behind it curve into arcs, smeared by gravitational lensing. The black hole itself emits no light, but around its edge may swirl a faint accretion disk, remnants of solar matter it consumed. This ring may glow with dim X-ray radiation, visible only through specialized instruments. And perhaps, just briefly after the black hole replaces the sun, a relativistic jet bursts from its pole, an energetic beam of matter and energy, shot across light years. These jets, powered by magnetic fields near the event horizon, could wreak havoc on nearby planets, depending on their orientation. If Earth is caught in such a blast, it would sterilize the surface in an instant. Let's suppose we survive the initial chaos. Let's suppose Earth stays in orbit, not flung away, not pulled in. Could we adapt to a sunless world? In theory, yes, but the world would be unrecognizable. Humanity would need to retreat underground or underwater, using geothermal or nuclear power to survive. Artificial lighting would be necessary for food production. Cities would need to be pressurized, insulated, and completely self-contained. Over time, entire civilizations might evolve without ever seeing sunlight. The stars would become the only guide. Astronomy would still exist, but with a painful awareness that the sun is no more. The concept of day and night would vanish. Timekeeping would become artificial. Circadian rhythms, mood, and biology would need to be chemically managed or engineered. Outside, on the surface, the world would be coated in silence and snow. No sound, no wind, just the occasional rumble of ice cracking under its own weight. Any remaining life would either be deep below or locked in stasis. Could we build cities around the black hole itself? Some futurists suggest a possibility, constructing Dyson spheres or rings around the black hole, not to capture light, but to harness gravitational energy or the emissions from infalling matter. This concept, though theoretical, is mind-boggling. By dropping mass into the black hole at precise angles, energy could be extracted via a method known as the Penrose process. Theoretically, this could provide immense power for advanced civilizations. But the engineering challenges are astronomical. Materials would need to survive tidal forces and extreme radiation. Energy transfer systems would need to stretch millions of kilometers. Stability would need to be actively managed to avoid collapse or collision. And all of this would need to be constructed while the solar system is dying. But the concept remains tantalizing. If we couldn't stop the black hole, could we live with it? Could humanity, in its most advanced form, learn to harness a black hole as its new sun? Could we orbit it with vast stations drawing power from its mass? Could we throw in captured comets, asteroids, or entire moons to create glowing flares of radiation to warm orbiting habitats? Could we become shadow dwellers, living not in sunlight but in the penumbra of gravity? There is precedent in science fiction. Civilization clinging to the edge of a black hole, drawing energy from its fury. Ring-like habitats orbiting just far enough to avoid tidal death, yet close enough to capture energy. Perhaps, in some distant future, humanity may not need sunlight at all. Perhaps we could become a species of black hole engineers, forging homes around these ancient beasts instead of fearing them. But for now, that remains fantasy. In our current timeline, if a black hole replaces the sun, the solar system becomes a dark machine, a ghost system. Planets orbit in silence. Moons drift like memories. And at the center of it all, where once warmth radiated outwards, there is only a well, deep, endless, inescapable. The sun gave life. The black hole takes it. Time is not absolute. It's not a constant, universal clock ticking evenly across the cosmos. It's elastic, dynamic, shaped and warped by gravity and speed. And nowhere is that more hauntingly evident than near a black hole. As Earth orbits closer to the singularity now seated where the sun once stood, the very nature of time begins to collapse around us. This isn't metaphor or theory. It's a cold, calculable truth. The closer you are to a black hole, the slower your time flows relative to the rest of the universe. This is known as gravitational time dilation, a key prediction of Einstein's general relativity, and it changes everything. Imagine two people. One remains in orbit around the black hole, at a safe distance. The other dares to descend toward it, skimming just above the event horizon. For the one approaching the black hole, time seems to pass normally. A second feels like a second. A heartbeat feels like a heartbeat. But from the perspective of the distant observer, that second stretches into minutes, hours, perhaps even years. The closer you get to the event horizon, the more extreme the time lag becomes. Near the edge of a massive black hole, an hour for you could be a decade for someone else. This idea isn't just a thought experiment, it's been confirmed experimentally, on small scales. Satellites orbiting Earth experience time just a tiny bit faster than people on the surface. GPS systems even correct for it. But near a black hole, this becomes pronounced. Dramatic. Life-changing. In our scenario, as Earth spirals closer to the black hole's influence, vast swaths of the planet begin to experience this effect. Days stretch. Years in orbit near the black hole may correspond to centuries or millennia in the rest of the universe. The deeper into the well of gravity we fall, the slower time flows for us. What would this feel like? To people living on the Earth, or in stations orbiting near the black hole, nothing seems wrong. Your clocks tick. Your speech flows. Your thoughts feel normal. But if you could peer outward beyond the bubble of warp time, you would see the universe racing ahead. Stars would appear to accelerate in their life cycles, aging, dying, vanishing. Distant galaxies would shift their shapes as billions of years pass. Civilizations, if any exist, would rise and fall in the blink of your eye. The cosmos outside would become a blur. You would be a living time capsule, frozen in slow motion, while everything else burns through the ages. This creates bizarre, surreal implications for communication. A message sent to you from outside might take seconds to arrive from your perspective, but you could never answer fast enough. Your reply would take decades or longer to reach the sender, if they're even still alive. Every conversation becomes one-sided. Every signal becomes ancient history by the time it's received. And what about technology? Suppose a space-faring human civilization exists elsewhere, and they're advancing at an exponential rate. If you fall into time dilation near the black hole, you might live only a few years, while outside, humanity or its successors experience tens of thousands. If they notice you trapped in orbit, they may one day return, as beings of immense intelligence, carrying technology so advanced it appears magical to you. From your perspective, they left only recently. From theirs, you're a relic of the distant past. This strange relationship between distance, gravity, and time opens a terrifying possibility. Escaping a black hole's gravity may not be impossible, but escaping its time distortion might be. The closer you are, the slower you become, until you are frozen. A black hole, then, is not just a trap of space, but of time itself. In fact, from an outside perspective, nothing ever truly falls into a black hole. As Earth approaches the event horizon, it appears to freeze, elongating, dimming, suspended at the very edge. Light from Earth grows redder and dimmer due to gravitational redshift, eventually becoming invisible. But the image of Earth, stretched across space and frozen in time, may remain imprinted near the horizon for eternity. To those left behind, Earth never quite falls. To those on Earth, the universe simply accelerates away. This raises one final, haunting idea: black holes are not just tombs, they are time machines. Not in the sci-fi sense of jumping into the past, but in the sense of moving forward at extreme speeds, simply by waiting. Want to see the end of the universe? Hover near the event horizon of a supermassive black hole for a few hours, and when you leave, if you ever can, billions of years may have passed. Could this be used intentionally? Some have speculated that civilizations might use black holes to preserve knowledge, freezing time around their vaults. Others might wait out cosmic catastrophes by suspending themselves in warp time. But in our current situation, this power is not a tool, it's a prison. For Earth, time now flows in strange, fractured ways. People in orbit farther from the black hole experience faster time. Those on the planet's surface may live for what they feel is years, while entire star systems blink into and out of existence above them. Cities fall out of sync. Communication breaks down. Cultures evolve at different rates, or freeze entirely. A fractured civilization trapped in a bubble of slow time, staring out at a universe that's already left them behind. There may come a moment, if we are lucky, when a vessel far from the black hole returns. Perhaps an ark launched early on, with survivors or descendants of those who fled the solar system. They dock near Earth, whose people have only aged a few years. To them, the voyagers are myth made real, beings from a future so distant it's indistinguishable from magic. To the voyagers, Earth is a fossil of their origin, still orbiting the abyss, unchanged and ancient. This is what time distortion truly means. Not just the slowing of seconds, but the destruction of shared experience. The end of simultaneity. The fragmentation of reality. And in this final silence, perhaps we understand. The black hole does not simply consume matter. It consumes time. What if, after all the chaos and panic, the black hole never even enters the solar system? What if this cosmic juggernaut, this invisible monster hurtling through space, simply passes by, a distant shadow, too far to grasp us in its gravitational snare? In the grand scale of the universe, space is unimaginably vast. Even if a black hole drifts into our galactic neighborhood, the odds of it perfectly intersecting with the plane of the solar system are still relatively small. Black holes don't steer with intent, they obey the slow, quiet pull of gravity. And so, there's a real possibility that it doesn't crash through our planetary orbits or devour the sun. It just drifts past. The effects of such a near miss would still be noticeable, but not apocalyptic. As the black hole approaches, its gravity would subtly tug on outer solar system objects, nudging long-orbiting comets, stirring the distant Oort Cloud. Telescopes would spot out lensing effects, stars warping and bending behind an invisible sphere. Precision instruments might detect orbital anomalies in Neptune or Pluto, but to the average person on Earth, life would continue unchanged. In this version of events, humanity's response might resemble how we track asteroids or comets. Astronomers worldwide would race to calculate its trajectory, updating models as data pours in. The world would hold its breath for days or weeks, watching every new simulation. Will it hit? Will it miss? Will it graze Neptune, or slip silently past? Then confirmation. It misses. The black hole passes a few 100 billion kilometers from the Sun. Far enough to avoid capture. Far enough that its influence fades into the background noise of interstellar space. Like a ghost ship crossing a dark ocean, it disappears again, leaving no trace but trembling instruments and a collective exhale of relief across Earth. This near-miss scenario opens an unexpected door, scientific opportunity. Because a passing black hole, especially a small one, might allow us to study these mysterious objects up close for the very first time. Space agencies might launch rapid deployment probes to intercept the trajectory, hoping to measure its gravitational field, examine its accretion zone, or monitor Hawking radiation. These missions would be high risk, but the rewards could be historic. Our first direct encounter with a black hole, our first measurements from the edge of an event horizon. The knowledge gained could be profound. We might finally confirm or reject theories about black hole thermodynamics, spin, and charge. We might even refine the elusive unification of quantum mechanics and general relativity, one of the greatest goals in physics. But let's go even further. What if the black hole that enters our solar system is not massive, not even stellar mass, but tiny. So small that it's almost undetectable. This brings us to the fascinating concept of primordial black holes. Unlike the ones formed by collapsing stars, primordial black holes are theorized to have formed in the first seconds after the Big Bang. In the chaotic soup of particles and energy, fluctuations in density may have caused some regions to collapse under their own gravity before stars even existed. These black holes could be as massive as an asteroid, or as light as a mountain. Some might be as small as atoms, but incredibly dense. If one of these tiny relics entered our solar system, what would happen? First, they would be very difficult to detect. They would be invisible, smaller than a baseball, possibly even smaller than a proton, but with masses of entire mountains or more. Unlike stellar black holes, they wouldn't emit X-rays or create visible accretion disks unless they pass through dense regions of gas or dust. Their only interaction with the solar system would be gravitational, and even then, it would be subtle. If such a black hole passed through Earth, it might create a bizarre, localized gravitational disturbance. Buildings might shake. Seismic readings would spike. But unless it passed directly through a populated area, it might go unnoticed. There would be no impact crater, no explosion, just a tremor, perhaps a faint and strange blip in gravity. In fact, some theories suggest that if primordial black holes exist, a few may already be wandering through our solar system, now. Hidden. Silent. Harmless, unless they pass too close to a large planetary body. Could we harness one? Theoretically, a stable primordial black hole could serve as a power source. If safely contained, it could radiate Hawking radiation, a source of energy that would last for millions of years. It could drive engines, power starships, or provide thrust for space exploration. But this assumes we can control it. More likely, the encounter would serve as a reminder: not all cosmic monsters come to destroy. Some just drift. Their presence might humble us, forcing us to recognize how little we understand about the universe. The very idea of a tiny black hole wandering through our backyard, and not destroying it, forces us to think in subtler, more complex ways. Black holes aren't just devourers. They're part of the cosmic ecosystem. A harmless black hole would still leave behind a legacy. It would spark scientific revolutions. It might unify theories that have evaded physicists for over a century. It would force new questions about the nature of time, entropy, and even the structure of space-time. Some theories suggest that primordial black holes might even make up part of the elusive dark matter, the invisible mass shaping galaxies. In that sense, a tiny black hole might not be an invader, but a messenger. A whisper from the early universe. A piece of its earliest moments, crossing paths with us before vanishing into the deep dark once more. So maybe, in an alternate outcome, we don't face destruction. Maybe we face perspective. A close encounter with something ancient and immense, but not fatal. The kind of moment that leaves our species changed, not ruined. Wiser. More united. More curious. Perhaps even more respectful of the silent, invisible forces that have shaped our universe for 13.8 billion years. And when it's gone, we would stand on our quiet planet and look up at the stars with new eyes, knowing that, just once, a shadow passed through us, and let us be. After the fury, after the unraveling of orbits and the death of light, after the planets have either fled, collided, or been swallowed, what remains? What does the solar system look like in the aftermath of a black hole's passing? What we find is neither the orderly dance of planets that once circled the sun, nor total annihilation. What we find is a remnant. A scar. A new kind of system, cold, fractured, and strange. Yet, in the ruins, something begins to take shape. Something new. Something alien. At the center is the black hole, the silent ruler. It does not glow, does not burn, but its gravitational grip has replaced that of the sun. Around it, a warped region of space, dominated by intense curvature. If the black hole has consumed the sun entirely, it likely carries its mass. Or even more, meaning its gravitational influence still reaches out across astronomical units. If Earth survived, or some version of it, it now orbits this abyss. No more daylight. No more seasons. Just a cycle around a void, time bending at every point. The ice-encased planet drifts in eternal night, its surface frozen, its core perhaps still warm, its atmosphere condensed. But below that frozen surface, life might yet cling. Elsewhere, other survivors exist. Jupiter, if it escaped the black hole's hunger, might be on a twisted new trajectory, its moons scattered, its orbit elongated. Some planets may have been flung completely out of the solar system, cast into interstellar space. These lonely travelers, known as rogue planets, wander without stars, carrying with them shattered atmospheres, broken magnetospheres, and perhaps even dormant life sealed deep within. Yet some bodies may remain in orbit, if not the original 8, then fragments, moons, dwarf planets. The remnants of Mercury and Mars. Shattered chunks of Saturn's rings. The Kuiper Belt, shredded, yet slowly regrouping into icy debris fields. A new accretion disk may form around the black hole at the system's center. The black hole, having consumed vast quantities of gas and debris, could begin spinning this matter into a glowing disk of heat and light. The process is violent, chaotic, and brief on cosmic timescales, but it brings a kind of temporary light back into the solar system. X-rays, gamma rays, even visible light from heated particles swirling at relativistic speeds just outside the event horizon. A ghost of a sun. A shadow star. This disk could heat nearby regions, provide energy to orbiting bodies, even become the center of new planetary formation, much like the original solar nebula did billions of years ago. Over millions of years, cooled material could coalesce into new planets, birthed from the chaos. But these wouldn't be worlds of sunlight and warmth. They would be planets of darkness, orbiting a starless gravity well. These new worlds might be stranger than anything we've imagined. Planets tidally locked to the black hole, always showing the same face. Planets warmed not by sunlight but by geothermal activity, or perhaps by the faint glow of an accretion disk. Moons colliding to create new debris rings. A second-generation solar system, not born of fire, but of aftermath. And there's a chance, though speculative, that new forms of life might one day emerge here. Extremophiles already survive near hydrothermal vents in our oceans, completely independent of sunlight. If such organisms or their analogues had survived the black hole's arrival, sealed deep beneath Earth's crust or beneath the ice of Europa, they might persist. Over millennia, perhaps evolve. Perhaps adapt. Alternatively, new life might emerge in the gravitational wells near the black hole, in the high-energy zones near the accretion disk. Could strange chemistry arise in such places? Could exotic particles or radiation patterns become the basis for a different kind of biology? Even in the darkness, nature finds a way to build. But what if nothing remains? What if the black hole was massive enough, or chaotic enough, to consume everything? If every planet was swallowed, every moon obliterated, every comet flung into interstellar space, then the solar system is gone. Only the black hole remains, alone, moving slowly through the void. Its presence known only by the lensing of distant stars behind it. The memory of our system encoded in gravitational waves that ripple outward across the galaxy, faint signals of planetary deaths, orbital disintegration, and stellar consumption. Perhaps alien civilizations detect these waves someday. Perhaps they triangulate the source. A black hole passed here. Perhaps they come to study, and find nothing but a singularity, surrounded by silence. But even in that emptiness, not all is lost. In physics, information is never truly destroyed. The shape of the world, the spin of the planets, the structure of the atoms, they imprint themselves on the black hole's event horizon, locked in ways we do not yet understand. A cosmic archive. The idea that all that was, the warmth of the sun, the blue of Earth, the memories of life, might still be encoded in the very fabric of the black hole's boundary. This leads to a final, poetic idea. Perhaps the solar system is not dead. It has merely been rewritten. Its contents folded into space-time itself. And far, far in the future, when black holes evaporate through Hawking radiation, when the last sparks of mass dissolve into pure energy, the final whispers of what we were might be released into the universe. A burst. A signal. The ghost of a system set free. So whether reborn in new planets, preserved in frozen time, or remembered in the quantum patterns of a black hole's skin, the solar system lives on, not as it was, but as it became. Somewhere, far beyond the remnants of shattered planets and broken orbits, a black hole moves silently through the dark. It leaves no trail. No sound. No light. Just a silent wake of warped space and altered time. And as it recedes, either because it passed us by, consumed us, or merely replaced what once gave us life, it leaves behind not only devastation, but a profound realization. We were never alone in the solar system. Not in the sense of aliens or civilizations, but in something deeper, cosmic forces we barely understand, lurking invisibly, governed by laws we did not write and cannot negotiate. We have spent millennia worshipping the sun, fearing comets, naming constellations, and mapping planets. But all that time, the black holes were watching. Not with intent, not with malice, but with gravity. Silent. Patient. Eternal. The black hole that visited our system was not a villain, not a monster in the traditional sense. It was a natural consequence of the universe's own evolution. It was the ghost of a dead star, the leftover kernel of collapse. A thing not born evil, but indifferent, utterly, inescapably indifferent. Its hunger is not emotional. Its destruction is not cruel. It simply is. And this is what makes it so terrifying. Because unlike an asteroid, it cannot be seen. Unlike a rogue planet, it does not reflect light. It offers no warning save for subtle distortions and the trembling of stars in the sky. And when it comes slowly, quietly. And then, everything changes. We are used to living in a solar system defined by balance. Orbits, gravity, fusion, and light. But that balance is delicate. The introduction of a single object, especially one as exotic and massive as a black hole, can tear the whole structure apart in mere moments on a cosmic scale. What has been stable for billions of years can unravel in thousands, hundreds, or even days. And yet, this event, as terrifying and destructive as it might be, is not unique. All across the galaxy, systems are being disrupted by passing objects, gravitational interactions, stellar deaths. Planetary systems far older than ours have already been lost. Entire galaxies have merged, throwing stars and worlds into new paths. And black holes? They are everywhere. Lurking at the hearts of galaxies. Drifting through interstellar space. Perhaps watching from the edge of our Oort Cloud right now. They are the ultimate reminder that space is not a safe place. It is vast. It is ancient. It is beautiful, yes, but it is also indifferent. And black holes, in their quiet, hidden power, are the perfect symbols of that indifference. No warning. No sound. No light. Just a sudden tug on the fabric of reality. Just a shadow that passes through, changes everything, and keeps going. And after it leaves, the silence returns. Maybe we survive. Maybe we don't. Maybe we're remembered, or maybe not. But somewhere in the galaxy, light from our sun, now long gone, will still be traveling outward. Echoes of what we once were. Stories written in photons. Even after the black hole, that light continues, crossing interstellar distances, passing by distant planets, grazing the edges of unknown civilizations. Perhaps, in some far-off future, a being will detect a faint signal buried in that light. A pulse of energy, a rhythm of days and nights, a whisper of life. And they will wonder what kind of star once shone here. What kind of world circled it? What kind of species looked up at the sky and wondered, as we do now, if they were alone? And maybe in that moment, they will understand. We were here. We lived. We dreamed. And once, a shadow passed through us, and moved on. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.